Hello. I hope I am audible. Okay. Yeah. So, hello everyone, and welcome to Fire 2020. So, given the situation that we all are in, and due to the pandemic, we had to take the entire conference into virtual mode. But still, we have overcome our situation, and we have been able to start this conference in virtual mode. So I thank everyone who is here today in the meeting, as well as who are seeing it on the YouTube live. We thank you everyone for joining us and supporting us in this conference. And I hope that everyone joins us again and again as we go ahead. So this is the 12th edition of the conference, and we have many interesting events over the next 5 days, 16th to 28th. This time, for the first time, the Fire conference had 10 tracks, and on an average, we had 60 participants working on all the tracks. And this year, we are going to have 4 plenary talks by Adam Weiner, Dr. Adam Weiner, Dr. Paul Clow, Dr. Ellen Burris from NIST USA, and Ajit Balakrishnan, Mr. Ajit Balakrishnan from Rediff.com. So, and we have a total of six conference papers in our conference track as in Fire 2020. So, uh, yeah, so let's begin with the conference. And so today we have the track overview session first, and the first, I'm announcing the name. So the first track is on track overview presentation is on artificial intelligence for legal assistance, and the presenter is Paheli Bhattacharya.
Hello, am I audible to all?
Yeah, you are audible.
Okay, is my screen visible?
Yes.
Okay. Hello all, I am Paheli Bhattacharya. I will be presenting overview of the FIRE 2020 track, Artificial Intelligence for Legal Assistance. Common law is followed by around 1/3 of the world's population. It stands on the principle that similar facts or situations will yield similar results. There are two sources of law in such a system: precedents or prior cases, and statutes, which are the written laws. Which means that when a legal situation comes to a law practitioner or a common man faces some legal problem, it will be beneficial to have an automatic system that identifies relevant prior cases and statutes that can be best suited to the purpose in the given situation. Motivated by this, we present two tasks in ILA 2020. The first one is the precedent and statute retrieval given a factual scenario as the query. This is a continuation of the ILA 2019 track. The second task we introduce in ILA 2020 is the rhetorical role labeling for legal judgments task. So the first task we divide into two parts. Task 1A is the precedent retrieval given the query. We received 26 runs from 10 teams. Task 1B is the statute retrieval given the query. For this, we received 27 runs from 12 teams. For task 2, which is a rhetorical role labeling for legal judgments task, we received 21 runs from 9 teams. Most of the participation came from India and China. There was participation from Botswana, Europe, and Canada as well. We also had a mix of academics and industry participation this time. Coming to the task, so the first one is the precedent and statute retrieval task, which is a continuation of the ILA 2019 track. In this task, given a query, which was a factual scenario written in natural language English, and it's kind of simulated a case description which comes prior to litigation. So given such a query, the task was to retrieve relevant prior cases, which we call precedent retrieval, and relevant statutes, which we call as statute retrieval. We considered documents from the Indian Supreme Court and statutes of the Indian judiciary. We provided the dataset developed in ILA 2019 as the training dataset, which consisted of 50 queries and 197 statutes. We added 343 more documents to the precedent documents pool, and there were 3257 documents in total. For the evaluation, we developed 10 queries, the gold standard answers of which came from the 3257 precedent documents and the 197 statutes. An example query is like this. So the query was like this. So a little girl was missing on a festival night. One day later, her dead body was found in a sugarcane field. And according to the doctor, the cause of death was cerebral hemorrhage resulting from head injury, and that the little girl had been raped before being killed. Given this query, the gold standard relevant precedents were these case documents, and the relevant statutes were the sections of the Indian Penal Code. An example is the IPC section 363, which defines punishment for kidnapping. So the evaluation measures we considered was mean average precision, precision at 10, BIPREF, and RECIPRANK. So coming to the results of task 1A, precedent retrieval, the best performing run achieved a map of 0.157. All the methods submitted were unsupervised. The training data we provided was mostly used to tune the hyperparameters. Embedding methods like dog-to-way glove were also used, but the performance was not that good. This is probably because these methods require a huge amount of data to be trained on. So this is a snapshot of the performance of the different runs. As you can see that the methods used, that is the last column, all the methods are unsupervised. Coming to the results of task 1B, that is statute retrieval, the best performing method achieved a map of 0.385, and this method used BERT. Actually, only one team used the training data to train the supervised models, which were BERT, LSTM, and a neural ranking model. The other teams used the training data to tune the hyperparameters of the different unsupervised methods they experimented with. Law-to-vec embeddings was also explored. This is a snapshot. Again, as you can see that the methods are mostly unsupervised. Only the first method, BERT, is a supervised method, and the other two supervised methods that were tried out did not perform well. Now we will talk about the second task, which we introduced in ILA 2020, which is the rhetorical role labeling for legal judgments task. Since case documents are long and usually unstructured, rhetorical role labeling or semantic segmentation enhances the readability of these case documents. It also has applications in several downstream tasks like summarization, semantic search, case law analysis, and so on. The different rhetorical roles we considered in this task was defined in a Jurix 2019 paper. So these labels are as follows. So the first one is facts, which is the chronology of events that led to filing the case. Ruling by lower court, which was the judgments given at the lower courts, like the High Court or the tribunal and so on. Arguments of the contending parties, citations to statute, citations to precedents, ratio of the decision, that is the rationale or the reasoning of the court for the final ruling. And lastly, ruling by present court, which is the final judgment given by the court. The task here was to label each sentence in a case document with one of the 7 rhetorical roles. In this task, we considered documents from the Indian Supreme Court. So for the training dataset, we use the publicly available dataset. It consisted of 50 documents from 5 law domains: constitutional, criminal, land and property, intellectual property rights, and labor and industrial. There were 9380 sentences in total, which was labeled with one rhetorical rule. The test dataset comprised of 10 documents, similarly from two documents each from these 5 law domains. And there were 1905 sentences in total, each labeled with one rhetorical rule. For the evaluation, we used macro average, precision, recall, and F-score. So coming to the results, the best performing method achieved an F-score of 0.468, which used Roberta plus logistic regression. We saw that BERT was applied by almost all the teams, coupled with different classifiers like logistic regression, a fully connected layer, and so on. There were also traditional machine learning approaches like SVM, random forest, etc., right? Using a bag of words based feature vectors. Not so surprisingly, deep learning methods performed much better than the machine learning approaches. So here is a snapshot of the different runs. As you can see, all the methods are mostly BERT based or Roberta based. So to conclude, we saw that the tasks are really challenging and we have a lot more work to do in this direction. An interesting thing, we saw that one of the teams that participated, LawNix, is a startup working in the legal domain and consists of a mix of lawyers and techies. This is what ILA really wants to target, bringing together multidisciplinary teams. As a future work, we plan to extend the gold standard, especially for task 1. We want to do that through pooling from the top results written by the team, written by the different runs. I would like to end my talk acknowledging the annotators, all the participating teams, and finally the FIRE organizing committee. Thank you.
Thank you, Payali. Next, we have, okay, so are there any doubts from the questions from the audience? All right, okay. Thank you, Payali. Yeah, so the next presentation is by on authorship identification of source code by Ali Fadel.
Hello, everyone. I just need to share the screen. Okay. Can you see my screen?
Yeah, it's visible.
Yeah, okay. So hello, everyone, and welcome to AI SOCO track overview paper presentation written by Ali Fadel, Hussam Masleh, Ibrahim Tufaha, Mahmoud Al-Ayyubi, Yasser Jarwa, Al-Hajj bin Khalifa, and Paulo Rosso. So I will start this presentation with the dataset. Our main source for the data was Codeforce's website. Codeforces is an online judge that has a lot of problems where users required to write a code in any programming language available on the website to solve the given problem. As an example, this is a very simple problem from Codeforce's website that requires the user to capitalize the given string by capitalizing the first character. Each problem has time and memory limits, as you can see in the screenshot here, and has problem statement, input and output format, and some examples, as you can see in the body of the problem here. These are sample solutions for the previously mentioned problem from 3 different users. As you can see, each user solved the problem in his/her own way, and the overlap between their solutions is minimal. As you can see in the solution in the right, for example, there is a lot of statements, and in the solution on the left, there is only 2 or 3 statements for input, output, and doing the logic for solving the problem. And to crawl the data that required for our task, we used the following criteria. We selected the first 1,000 users with 100 accepted solutions or more that written in C++ programming language with any compiler available on the website. And we applied a time criteria to choose the 100 solutions submitted by each user by selecting the closest 100 solutions in the timeline of a user's submissions, as shown in the example in this slide. So, for example, here, if user A submitted a solution in each red vertical line, we chose the closest 100 solutions and chose them as our dataset. By this time criteria, we maintain the stability of the user's code style as much as possible. These are some statistics about the collected dataset. As you can see, we have 1,000 users with 100 solutions per user. So in total, we have 100,000 solutions in our dataset. The solutions came from about 6,500 unique problems on Codeforce's website. So the dataset is diverse in terms of problem type and the used technique or algorithm to solve it. Also, the dataset contains solutions from users spread on like 78 countries. So we don't bias to a specific country code style. And finally, the dataset has millions of non-white space tokens. As you can see in this slide, the website users prefer to use GNU C++ compilers over Microsoft compilers in general. So the number of solutions in GNU C++ 11, 14, and 17 is the dominant. Another feature in Codeforces is the problem index or difficulty. This chart shows the number of problems per index for each problem. So normal competitions in Codeforces platform contain 5 to 7 problems indices indexed from A to G. So as you can see, other indices has very low number of solutions, and the reason is not only the rarity of them in the website, but also about their difficulty level. So problems with index more than F are very difficult, and not all users can solve them. Here we are defining our task. So simply, given the predefined list of source codes and their writers, you need to build a system that can identify the writer of any new and unseen before source codes from the previously defined writers list. So as an example, if we built the system using source codes A, B, and C written by users A, B, and C, and then we passed a new source code D to the system that written by user B, then the system should predict the writer correctly. We created 6 baselines for this task. The first one is a random baseline, which has accuracy about 0.1% on development and testing dataset. The next 2 baselines are simple baselines using machine learning techniques like logistic regression and TF-IDF with KNN to build the source code representation and predict the writer. Finally, the last 3 baselines were built on top of Roberta-like transformer. We pre-trained the model on our training dataset. After that, we fine-tuned the model on the downstream classification task. The main difference between the 3 baselines is the size of the model. In the first one, we used 1 transformer layer with 12 heads, while in the second one, we increased the number of attention heads to 96. Lastly, we used 6 layers with 12 heads in each of them to build our last baseline. Here I am listing the top 10 teams from our competition. As you can see, 8 out of the top 10 teams achieved accuracy higher than 90%, which is very surprising for us. We thought that the problem is very difficult, but actually it was pretty much easy to solve using the power of n-grams, which is the name of the first team's paper, which is UOB team, that achieved a very good results using a simple approach that combined n-grams occurred to build the source code representation and a simple feed-forward neural network to predict the writer. And also all other teams used the n-grams approach and counting occurrences of n-grams to approach this problem. At this end, thanks for attending and listening. Do you have any questions?
Thank you, Ali.
Yeah, thank you.
Yeah, okay. So the next presentation is on cause-effect relation extraction from text by Tirthankar Dasgupta.
Hello, am I audible?
Yes, you are audible.
Yeah, okay. And I think my screen is also visible.
Yes.
Okay, so yeah. So good afternoon, everyone. I am Tirthankar Dasgupta from TCS Research and Innovation Lab, Kolkata. And I am going to give you the brief overview of the shared task on cause-effect relation extraction, which is floated for the first time in FIRE 2020. So the co-chairs of these tracks are Dr. Manjita Sinha and Dr. Lipika De. Dr. Manjita Sinha is from IIT Kharagpur and Lipika De is from TCS Research and Innovation Lab, Delhi. So the main, actually, to give you a brief idea about what causality or cause-effect relationship is, so causality is a relationship between two events, E1 and E2, where E1 results in the occurrence of E2. So, say for example, given a particular sentence like Toyota recalls 1,500 cars into faulty airbag, you can understand that, I mean, the cause is, the effect is the faulty, the effect is Toyota is recalling around 1,50,000 cars, and the corresponding cause is due to its faulty airbags. So identifying such kind of cause and effect relationship, I mean, this kind of semantic relationships are essential for different type of use cases, like for example, building knowledge graphs, or in other many of these analytical and predictive applications. So particularly in knowledge graph, we need to have, we need to extract a lot of these kind of cause-effect event pairs which are semantically related. Then there are many other tasks associated. For example, identifying similar kind of causes, similar kind of effects, and then grouping them together to finally form a knowledge graph, which is usable by the different type of applications. So it is also important for different type of analytical and predictive applications like early warning systems, where you need to trace different type of events that are occurring across different geographical locations. You need to infer them, and then you need to predict that what are the possible effects or side effects that are going to occur. So with respect to this, I mean, we floated this cause-effect relation extraction task, where in the data set also, I mean, we have observed that there are different type of causal relations exist. So the most simpler one is the marked causality. I mean, so in literature also there has been several type of mentions of this type of causal relationships, like the marked and unmarked causality, where specifically causal connectives are present within a sentence to denote that what are the causes and the effects. There are examples of unmarked causality where explicitly there is no mention of the causal connectives, but still the human can very easily identify that what is the cause and what is the effect. For example, the sentence drive slowly, there are potholes. So here you can see the connectives or the causal markers, like causal markers are not explicitly present, but still we can understand that there is a causal relationship exists between these two events. There are other type of causalities that are explained in the literature, like explicit and implicit causality. So where the cause and effect can may not be explicitly present in a sentence. So there can be an effect mention and the cause has to be interpreted by the human reader. And finally, there are situations where there are chain of events, particularly in different kind of textual mentions. So one event may lead to another event, which may lead to another event. So there are different type of such kind of manifestations, like an event E1 can lead to multiple events E2, E3, E4. Multiple events can lead to a single event, multiple and or there are situations like where events are linked in terms of temporal factors, like an event E1 occurring in time T1, which may lead to event E2 in a time T2. So these are the different type of manifestation of these cause-effect relationships, which are there in different kind of textual data sets or textual data which are normally there in the social media texts. So with respect to this, we have defined two different tasks. So one task is, given a particular sentence, we need to identify whether the sentence is causal or not. So this particular task, maybe initially we thought that it to be a very simple one, but we observed that typically we haven't got a very high accuracy by the participants, mainly because of the fact that there are many ambiguities within the sentences which may lead to fail the model. For example, in the sentence like the tornado caused destruction followed by the widespread disease, here followed by is a causal explicit causal marker, whereas the same marker when used in sentences like the leader was followed by his supporters in the march, here actually this phrase is not acting as a causal marker, and typically we have seen that models do fail. So this makes this task not a very trivial one. The second task is, so given a particular causal sentence, can we identify the exact cause and effect and the connective phrases? So, which is quite understandable. So essentially we have got 4 different classes, and we consider this problem as a sequence leveling task, where every individual word of a sentence has to be tagged into any one of these 4 classes, which is cause, effect, connective, or none. So say for example, in this particular sentence, like in developing countries, 4/5 of all the illnesses are caused by waterborne diseases. Here the initial words like in developing countries are not a part of either cause or effect or any connectives. So they has been tagged as N, N, and N. Whereas 4/5 of all the illnesses, these are the effect, are caused by waterborne diseases. So waterborne diseases are the cause. 4/5 of all the illnesses are the effects. So in this way, the model has to annotate. Model has to label the input sentences. So, so we have collected dataset, raw dataset from raw as well as some tag and tag annotated dataset from different domains. So our objective is to collect as many different sources as possible. So the first source is SemiVal task, SemiVal 2010 task. So where different type of cause and effect relationships are marked. Now, in this particular data set, you will see, these marking of these cause and effects are typically word-based. So, say for example, the AIDS pandemic caused by spread of HIV infection. Here, on that particular task, only the different words are marked. So, pandemic is an effect and infection is the cause. Whereas we have seen that more accurate annotations can be done with instead of words, if we can take the phrases. For example, infectious disease or communicable diseases are caused by bacteria, viruses, and parasite. Here also, we have seen that in SemiVal, the annotation is in the form of infectious disease and as effect and bacteria as cause. Whereas we have annotated the same sentences as infectious diseases or communicable diseases as the entire phrase as effect, and the bacteria, virus, and parasites, the entire phrase as cause. So this gives a better representation of understanding of the entire the cause and effect events. So secondly, given a sentence, complex sentences, we try to break them into simpler sentences so that the model can perform better. For example, so I will give that example later on. So here, given a particular sentence, so we have 3 different annotators who have manually verified each and every individual sentences, and then they have been assigned 2 different tasks. One is that identify whether any causal connectives are there within the, whether the sentence is a causal sentence, and second is, given a particular sentence as causal, can you identify the cause, effects, and the connectives from that particular sentence. So in this particular way, this is an example sentence and its corresponding annotation that has been done by the annotators. So apart from this, there are many other post-processing we have performed before giving it to the participants. One is for complex sentences, we have split it into multiple simpler sentences. So there are 2 different cases can be there. So one case is that one sentence may contain multiple cause-effect pairs, which are about these cause-effect pairs are separated. So for example, in this particular sentence, in developing countries, 4/5 of all the illnesses are caused by waterborne diseases, with diarrhea being the leading cause of child death. So here you can see there are 2 different causal information are there. One is diarrhea being the leading cause of child death, and another is in developing country, 4/5 of all the illnesses are caused by waterborne diseases. So we asked the manual annotators to especially take this type of long complex sentences and break them into 2 different chunks, and then you try to annotate them together. So essentially we are getting smaller individual chunks containing only single causal elements within a single text or within a single sentence. The second scenario is little bit complex, where a single sentence may contain a chain of causal event that I have explained before. That, say for example, attrition of associates will affect scheduled release of product, which may cause high business impact. So here you can see an event E1 is causing another event E2, which is further leading to event E3. So here in these cases, I mean, the annotators have marked all the possible things, I mean, with respect to numberings, that which part of the sentence is a cause one, which is an effect one, and which cause is corresponding to which effect, and which and so on. So in this way, the annotators have annotated these sentences, but we observe that this kind of situations may become a little bit difficult for a model to handle. So specifically for this task, we have manually removed all these complex sentences. I mean, particularly these case 2 scenarios. So we have got I mean, there are two, all the registered teams, only 2 made it to the final submissions, and they have submitted all the different individual tasks with the working notes. So, and one team is from within India SSN College of Engineering, and another team is from University of Chittagong, Bangladesh. And so both these, so the approaches that they have taken, I mean, you can, if you are interested, then you can visit their presentations, which will be tomorrow. So given this particular model, so we try to evaluate the output of these models with respect to 3 different parameters: precision, recall, and F measure. So for that, we have released a separate test data set, which is not annotated to them. I mean, and then we have posted this held out data set without the target level during this evaluation phase, and then we have computed the accuracies. So these are the typical results that are obtained by these individual teams, and we found that for task A, the best result was returned by the Chittagong University, and for task B, the SSN NLP group has got a higher F1 score, but typically for both of these tasks, we found that the overall accuracy of the system is pretty low, particularly for task B, which is quite understandable because task B is a bit more complex. So yeah, this is all about this particular track, and if you have any other questions, you are free to, will be happy to answer. Thank you.
Yeah, thank you, Tirthankar. If anyone has any doubts in the audience, then they can raise their hands in the Zoom emoticon feature, and I will unmute them. Okay. Okay. Thank you, Tirthankar. Yeah. Okay. So next is okay. So the next is causality-driven ad hoc information retrieval by Devashish Ganguly.
Hello, can you hear me? Hi, can you hear me?
Yes, you're audible.
Okay,
Yeah.
let me try to share my screen. Wait a minute. Is my screen visible now?
Yes.
Okay. Let me try to do the full screen thing. Let me see if it works. Okay, it doesn't work. Okay, so let me start the presentation. So this is the track that we organized in FIRE 2020. So this is on the causality-driven ad hoc information retrieval task that was co-hosted by me and Shuchana and my colleagues from IBM and Doipan and Derek Green from UCD. Sorry. Okay, so the outline of my talk is going to be like this. I'm going to start with the motivation of the track, and then I'm going to describe the tasks that we proposed for this track, the data sets that we released, and we'll talk briefly about the approaches that the participating teams applied for getting the results in this track. I'll briefly provide an overview of the results. I'm sure you can listen to the talk tomorrow from the participating teams themselves if you want to listen more about their approaches. And finally, I'll conclude with some takeaways. So the motivation of this track basically came from our CIR paper, which came out this year. So the paper was basically about trying to investigate the question that, in contrast to ad hoc IR, where you specify a query and then you need to retrieve a list of documents that satisfy the information need expressed in that query. In contrast to that, what we aim to develop is that, given a query, we don't really need we don't really need the relevant information for that query itself, but we want to find out information that could have led to that specific event described in the query. So as examples, let's consider the query, what are the reasons behind assassination of Osama bin Laden? Now, there's one difference of this work, with typical, causality-driven approaches in NLP, like the previous talk that Tirthankar mentioned. So there, you typically have, within a sentence, you have some basic causes. For example, like, tsunamis can cause earthquakes. You might find that within a single span of a sentence or within very close sentences. So these are very atomic events for which, it's essential, or you could build up knowledge bases, for this kind of very atomic kind of, causality, cause and effect relationships. But instead of that, what we are looking here is we don't really intend to address these very fine-grained cause and effect relationships. So what we intend to do is that, in our case, we specify a query, and then we intend to retrieve documents, for which, so there could be like multiple possible causes that could have led to that event. So say, for example, in this case, the death of Osama bin Laden. Now there could be, arguably, there could be many different factors that could have led to this particular event, right? So if you trace back in history, you might think that, there were, political unrest in the Middle East, and then there was this terrorist attack on USA, and then there are so many other factors, that you could argue that could have caused, could have led to the situations that have, led to the death of Osama bin Laden. So we don't expect to find everything within one single document, because it's not something like a known item search. We could have multiple documents, where we could have relevant information spread in the multiple documents, and that makes this task challenging itself, because you might lose out on the recall, right? So you'd want to retrieve all the pieces of information that you could find, which might have caused the specific event that you mentioned in your query. So let's try to see more examples of that. So in this case, we know that Osama was killed by US Navy in 2011, but it's pretty difficult. I mean, if you want to, you may not know this fact, right? So if you just type assassination of Osama bin Laden, and if you want to see the causes, then it's really difficult, right? Because if you type in Google just this query, assassination of Osama bin Laden, it specifically gives information about the death of bin Laden itself. But to know, what were the causes you need to be knowing that beforehand in order to find those documents. Otherwise, it's really tough for you to find those documents, right? So in this case, so standard information retrieval systems could employ something like query expansion, and then, if you do that, then probably, you will find more documents about the death of bin Laden itself. But it doesn't really give you, it doesn't really allow you to get back in history and then kind of look into documents that were 15 years back in time. Because if you look into the overlap of these documents with the topical relevant ones, then probably we'll expect that there is not that much an overlap in terms of overlap of the topics. Possibly you won't expect a large topical overlap. So this is what so we could do. So in this case, as we can see, that we don't really find that much of useful information here, because these are all documents about the death of bin Laden itself. So, you may not be happy with that answer, right? So in this case, we could try to be more specific, and then you could type in queries like causes and have a query like this: assassination of Osama bin Laden, and then you could, add that term causes to this particular query of yours, in the hope that maybe including that term could give you the relevant documents. But in this case, it don't really help that much, because cause is a very common word, right? And if you just include this word, the effect that this particular word will have on the rank lists that's retrieved, it's not going to be that much. So we can try that out. So if you include this word causes, then also you find documents that are generally on bin Laden himself. You can see documents on the reactions of death of Osama bin Laden. So these are more like general documents, but even then, these are not really the causes that has led to the death of bin Laden. So it's not really adding something like a stop word, or adding something like a very common word like cause is not going to help that much. So this actually makes the problem challenging, right? So that was one of the motivations that we arranged this track, so that we could foster developing research that could actually try to investigate methods or models that could be useful to do this kind of searching. So yeah, I still can't find all significant reasons. So I think that this problem, it shows that the problem is not trivial one, and we need to build up data sets, and we need to investigate this problem more closely. So that brings us to the task definition itself. So basically, we want to find out where is the why, and for that, to promote research in this direction, we provide a data set comprising of a static test collection of documents and a list of queries related to events that are likely to be caused by a number of other past events. So keep in mind that in this case, our queries, do not comprise of those cases, where the causality chain is very fine-grained. So something like, as Tirthankar mentioned in his earlier talk, something like diseases, they are caused by bacteria, or they are mainly caused by waterborne diseases, or caused by bacteria in the third world countries or in the developing countries. So these could be very fine-grained relations or causal relations, which typically you will find in one single document, maybe in the headline itself, or maybe within one single sentence of a news article. So that's something that's something that we did not want to include as a query, because we wanted to have those cases where there could be multiple arguments and then multiple factors that could have led to a particular query event. So something like the death of bin Laden is a perfect example of such a query. So we released 25 queries as a test set, and the participants were to develop ranking models to effectively retrieve documents. And then we already started with some relevance judgments, or the set of relevance judgments that we already had, and that came from the Sigaya paper. And by submitting runs, we would have been able to compute how effective were those rank lists of documents. So data set comprised of telegraph dump, which is a news article or a newspaper, an English newspaper from India, published from 2001, 2011. So we crawled these documents from this time of 10 years. And that was the collection, or that was target collection that we had. And these news comprised of different categories like business, sports, front page, nation, etc. So in total, we had 303,000 documents, and the vocabulary size was something like 700,000. And we compiled 25 topics from the FIRE ad hoc query set. So we used, as I mentioned, that we made sure that the selected query event must have a number of factors responsible for leading towards that particular event. And we excluded cases where the causality factor is either too obvious or too small in number. So we did not want a case where you had a very small number of relevant documents. And then the selected topic must occur during the period covered by the target collection, because if it's not there, then probably there is no way of retrieving those documents, right? So if the particular cause that you are trying to find that does not span the target, that does not span the time span of the target collection itself, then we can't perform these experiments in a laboratory-based condition, because we are restricting our target collection to a specific set of documents, right? So something that does not belong there, we can't retrieve that, and probably there is no point of including those queries. So that's something that we ensured as well. And then for each query, we have relevance judgments. So basically, the relevance judgments that we are used to in standard IR, they will correspond to the topical relevance, to the notion of topical relevance. That given a query, something like assassination of Bin Laden, we want documents that basically talk about that topic. But in this case, we had to bear in mind that the relevance notions, is different, right? And that's something that we kept in mind, or we had in mind, while annotating the relevance for these documents. So it's something that if that document talks about a potential cause that might have led to that particular event, then we mark that document as relevant, or else we don't mark it as relevant. So this has to be kept in mind, that the set of relevance that we obtain through our annotation process, that's quite different from the standard notion of topical relevance that you typically find in ad hoc IR. Okay, now since we already started with a set of relevant documents, so this came from the CIR paper, but then as an outcome for this track, we wanted, because we expected that we'll receive runs from the participants, and a standard way to extend the set of relevance judgments is to employ something like pooling. So in a pool, you basically take the top 50 or top 100, this number being called this depth of the pool. So the typical value of the depth could be 50. So you take the top 50 runs from each participating system, and you compute the union, and then you dump that in your pool, and then that's something that you throw into the assessors for judgments. So that's something that we did. So we took I think the top 25 runs from the participants. We comprised this union set, and then we asked assessors to look through these documents and then mark the causal relevance for these documents, not the topical ones. So this is a graph which shows that for each of the runs we included, or how many of the documents from each run actually made to the pool. So we can see that we actually got quite a few number of new relevant documents from the participants run. So this is something that is a takeaway, that if we organize a track like this and ask participants to submit runs for the queries, even if you already had a few number of relevant documents for the queries, well, it's possible to extend that relevant set if you have more documents coming into your system. So we had two participating teams that participated for this task. So the first team was from University of California, Santa Cruz, and the second team was from National Institute of Technology, Silchar, India. So roughly speaking, the first team did something like, so they had a pipeline where the first step involved retrieving this causal relations from documents, right? So you typically do an event extraction, and then after the first retrieval, you typically try to find out the causes, from those documents, and then they use these terms then to feed into the query expansion, for the second retrieval. So I'm sure you could listen to their talk tomorrow, to get more details about the specific details about what kind of models did they use for causality extraction from. So how did they extract the events, and what are the models that they use for extracting causes from those events? You can listen to their talk tomorrow. And the team B from NIT Shilchar, so what they did was they tried to embed sentences, with something called an universal sentence encoder. So basically, you feed in sentences and you get vectors, and then they use these vectors to kind of compute similarities between the causes and the events. And they use this for ranking the documents. So I could quickly walk through the results of the teams. So the team from UCSC, University of California, Santa Cruz. So they obtained, so the map values that they obtained were a lot higher than the maps that were obtained by NIT Shilchar. So I guess one of the reasons was that this team from UCSC, they used longer queries. So they used so in the query itself, there was the title field and the description field. So I think they used the description field as well, and that might have helped in finding better terms, for query expansion, and to be able to find documents that showed causal relationships with the query event. And so this might be a takeaway, because if you can find, or if you can find terms that are more related to your event, your query event, it might actually help you to find better terms that could describe your causes, and that could help you in getting better retrieval performance. So the conclusion is that we are the submitted runs that actually gave us insights that event extraction is beneficial. So as I said, if you are good at extracting the event, and then if you are able to expand that semantically, and so that might actually help you to retrieve more potential causes. And one of the other takeaways is that we established a data set for the research community, and this is the first of its kind, because these causality events that we are talking about here, these are not that fine grained. So these are like coarse grained cause and effect relations. And this challenge here is to find causes from multiple documents. So in terms of NLP, this is somewhat analogous to the co-reference resolution from multiple documents, because you are not restricting yourself to one single document, but then you want to go back and trace into other documents and then find the potential causes from those documents. So with that, I will end my talk, and then I'm prepared for any questions that I might have. Thank you.
Thank you, Devashish. Any questions from the audience? They can directly unmute if they wish. All right. Okay. Thank you, Devashish. We now take a break of 10 minutes and we return back. The next presentation will be on hate speech and offensive content identification in Indo-European languages. We take a 10 minutes break and we will be back online again. Thank you. Okay, so let's move ahead. All right. Next presentation is on hate speech and offensive content identification in European language by Thomas Mandel and Anand Kumaran.
So thank you, Surupendo, for the introduction. Welcome to the crowd on Zoom and to the YouTube crowd. Welcome to the HAZOC presentation. I also thank all the supporters here, all the volunteers that have done such a lot of work to make this happen from several institutions. So it was very nice to organize this. And yeah, hate speech is a big social issue in many countries, and we considered for HAZOC this as a multilingual and multi-class classification problem, and we wanted to work on social media and offer a track for the identification of problematic content for different types of social media and different languages, as you will see. And we have continued from 2019, and we also extended. We got 2 Dravidian languages. This subtask will be presented after my talk from Bharati or Anand Kumar. And we continued with the 3 languages that we had last year: English, German, and Hindi. This is the overview. We will talk about the task. How was the annotation done? What are the results? Some quick look at analysis, and then the outlook. So I got some background noise there. I'm not sure if everybody has that. I hope I'm audible well and others don't hear that. Yeah, subtask A was just a binary classification problem into problematic content that we called HOF, HOF, and non-offensive, non-problematic content that we called NOT. And in the second task, in the task B, people had to further subgroup, fine-grainedly classify the HOF class into hate speech, offensive, or profane. So hate speech is then attacking people or downgrading them because they belong to a certain group. Offensive is aggression against an individual. And profanity would be typical whatever pornographic content or other swear words or some profanity that we don't want to see on social media, that most people would consider to be not appropriate for social media. So here is the further detailed definition, which was available to participants, of course, but also mainly to the annotators who had to work on that. And here we see the different groups, the issues that can be used to label something as hate speech, and here something as offensive. How was the data collected? Here we applied a different method this year. The typical methods that we see in other hate speech tasks for other languages and other tasks, other competitions, is that people make up some words and search with them, and then try to find some hate-related words that bring them to some content that then can be used. And this, of course, is somehow limited by the words that we can make up. There might be other models of hate speech, other offensive words that we don't find. That might maybe not have such a huge impact, but of course, then the task does not cover the full spectrum of hate and offensiveness. And another task to avoid bias by users is another method that we applied last time, is to crawl the timeline of some users that have been identified with these related words. However, system in action, if a platform applies that, obviously this needs to be done, classified, before human looks at these tweets or posts. So it will be a pre-classification system, and some tweets that are identified as potentially hateful will be often checked by a human. So there will be human label in the second place. And we try to apply that in our data collection, data assembly this year. So we downloaded a large Twitter file from archive.org that is from the same time as the HASOC 2019 data. So we have some comparable content there. We trained a classifier with the HASOC 19 data plus another data set. For each language, we used another additional data set. You see that in the overview paper. And this classifier, we didn't use the very best classifier, so that we also want some, of course, not offensive tweets in this set. And this result was given to a human annotator plus 10% from the, actually not random, but from the negative class. So overall, the data set was then more or less balanced. So here we have a look at the annotation interface that our annotators had to work with, so several weeks to get all this ready. And of course, there's always some issues similar to last year. The text might not be offensive, but there is graphical content. There might be a lack of context. I cannot really judge this this text, the short text. There might be quotation marks that seem to make a comment out of that. And there can be irony and many other things. Youth talk is just might be accepted, this kind of language in one group, but maybe not in the large group. So several issues that make this assessment difficult from time pressure. And we see this is an example where two annotators have the different opinions. This is things that happen. We got some disagreement also. We see here some percentages. Overall, we think that the disagreement was in the same at the same level as last year. And in case we had the resources, we gave a second annotator to many of the tweets. And if the annotators agreed, there was of course no problem. If they did not agree, you see the numbers here. Then we used a heuristic judgment function. Either we had a third label, third annotator working there, but that could not be done for all of the tweets. Often we had to make a decision, and here we choose the annotator that seemed more reliable based on the overlap with the other annotators in the overall set. We had more than 10 annotators, between 10 and 14 for each of the languages. So we reached a set of this size overall. We have training data and test data. In addition, we have the development data that we call it, that is used to give submitters, the participants, feedback when they submit, so they can already have an idea about their performance. And we see in all sets this new sampling method that we think is very realistic leads to a large portion of profanity. So there is a large portion of profane tweets that somehow now dominate this sets. Oh, for next year, we have to see how we move on. Yeah, the competition was run on CodaLab. It was all set up and submitted, and we had quite some more participants than last year. Over 40 teams submitted some runs in the end, and 31 had submitted and accepted papers. So that is, unfortunately, we don't have a description of all submissions, but of course of the majority. And we see the countries that I found by a quick glimpse through the papers. India and China had the most groups, but there's also groups from Europe, South and North America. Let's come to the results. We have 3 tracks, and we see that for the Hindi task A, so the binary classification, we get quite low F1 score. And we see also the difference between these, let's say, top 10, top 15 runs is not very big. So maybe the development set has led to that, or other factors, not yet sure. But definitely there's a very small differences between all the runs in all the tasks. We see that in this case, for example, by LSTM made the best submission. Here we have a submission that even doesn't use deep learning, so it also can get to a similar rank. similar values. And here we have a bird model, a refined bird model on position 4. Hindi task B, we see the values for this fine-grained classification of the Hoff class are also quite low. We have very low F1 measures. We see again the BILSTM, the same group, has very good results here. And also CNN has performed well in this task. Let's move to the German task A. Here we see that bird models have gotten very good results overall. Also, maybe this could be a reason could be that maybe bird is there's a better bird model available for German. For the task B, again we see attention models, different versions of bird person attention model on the top, and same, we are in the same range of results of F1 measures, and we have also the same phenomena that we have a very low, a small difference between the top systems. English task A. Move on to English. We have in this case also the top system plus also system here in position 6 used an LSTM. So no bird yet, but of course also bird and other transformer models have led to very good results in the same F1 range. And for the English task B, we see again similar F1 scores, little difference. That's the same for all languages. And in this case, we have bird models on the top 3 positions. So is there any bias? That's always a question we have to ask ourselves. We did some checks last year. For this year, we haven't really gotten around. For the English model 2019, we see a very nice topic modeling result where 4 classes really do not overlap. And these are probably the 4 relevant topics that we have caught last year. And we see that they are present in both training, testing, and in all the, also in the Hoff and non-Hoff class with a similar extent. So that means at least there, a simple model predicting content wouldn't have worked for the hate speech detection. Yeah, future work, maybe there will be another edition, we will see. We definitely do also need to work more on research. We have to refine our collection process. The algorithmic support, I think, is necessary for the collection, definitely, and annotation. But we might have to check whether there is bias introduced and maybe move to a hybrid model for the next year if we all get together and organize this again. Maybe also more languages. There has been some editions already. And of course, we're open for new ideas. So put any questions or comments in the chat or ask with the microphone. Also in the YouTube chat, feel free to ask questions. So thank you all for your attention. Ready for questions. And then after that, the next subtrack of HAZOG will be presented on the Dravidian languages. Thank you.
Hi, Thomas. I don't know if I can ask. Paolo speaking.
Sure. Hi, Paolo. How are you?
Fine. How are you?
Of
Fine.
course, please
Thanks.
ask your question.
A lot of participants also this year in your task. Congratulations. So from what you showed in the 3 languages, the F measure was not so high, you said it. And of course, I guess you didn't have the time to go through, I mean, the results and to do an in-depth analysis. But what is your feeling, your intuition that could be the problem? The difficulty of the task, maybe data is noisy, maybe the difference between the categories is somehow fuzzy in some cases. So I was curious to know what is your very preliminary thought about it. Okay, danke.
Yeah. Thank you, Paolo. Very good question. I think there might be some noise in the data, probably especially for the subtask B. That is also very hard to annotate. Even after long discussions, we see disagreement if we work with annotators and sit down for task A, the participants reported much higher values in their papers on the training and also on the development set, as far as I remember. So what we have to do next is really to check, are there differences in the between the composition somehow of the development and the test set, which would be unexpected. There was a random split. All the data was already annotated, and then it was split randomly for these two sets. But we're unsure. Maybe there is some bias that has been introduced by somehow. And maybe as I said, this new collection process that we consider to be very realistic brought in a lot of profane content, a lot of pornographic content, and there might be an issue there. I don't know if that has really made the task more difficult or stranger for the systems. So that is something we will check.
Thanks.
Hi, Thomas. Can I ask you a question?
Please.
Yeah, so I was wondering that you are reporting F-score values, but I'm wondering about what happens to your precision and recall values. I mean, is it the case that most of the models are getting better results for precision, or they're getting better results for recall? Did you actually see that?
Good question, but no, we haven't looked into the details so far. We just had the chance to check the overall metrics, but that's a good point too. Yeah, looking at the recall and precision and see what is going on there, why are the differences so small, and well, this is what happens if we take out 10 documents. Maybe the positions already changed. That's something we have to check. Thank you.
Thank you.
Further questions? Maybe not at the moment. So thank you for your attention, and I hand back to Suru, or I hand back over directly to the Dravidian task, which also got a lot of response. So there is certainly great interest in the task.
Yeah, I think Anand can start his presentation.
Yeah, thank you. Is it visible?
Yeah, it is visible. Yeah.
Yeah, so thanks to FIRE and thanks to Thomas Mandel to is actually here, and Tamil and Malayalam. The remaining things are the thing. Hello, am I audible?
I think your voice got lost in between.
Okay, sorry. Okay, is it fine now?
Yes.
Okay, thank you. So I'll sit a little close. Yeah. 1 second. Okay, thank you. So I think, I hope you have covered the thing. So this is the outline. So I'll talk about a few things about the code mixing, and I'll directly go to the task description and data set description, and we'll see the participants system and then the results and conclusion. So as I said that, so he has given a nice introduction about the hate speech. So I'm directly going to the code mix, the other part of it, the challenging. So we are talking about the Dravidian code, as you've seen that the Dravidian languages are under-resourced languages. So we thought of taking that as a challenge and the one thing. So we don't have so much resources, and most of the text, online text or social media text are in code mixed. So we thought of using that, taking as a motivation of this chat task. So there is an increasing demand in the generally in the offensive language detection. So particularly in case of Indic languages, so the code mixing is the phenomenon where the country like India, so where people used to mix the languages and people used to write with the non-native scripts. Say for example, we try to cover the we try to cover the two different forms of code mixing in our task. The one is actually one kind of code mixing. You can say that it's like a cross script. So take Tamil or Malayalam language, so written using Latin script, completely written using Latin script, Latin or Roman script. So that's a one thing. Other thing is, in somewhere we come across that people used to mix the languages, mix the script. So say some comments will be maybe in pure native script, say for Malayalam, then some comments will be in English. So that also we have considered here in our task. So when we are talking about, as I said, that this is as far as our knowledge, this is the first gold standard corpus for offensive language detection in Dravidian languages. So as is the first time you are organizing this shared task in this area, so we have been annotated for finer. We have been annotated in a finer way, like how the Thomas Mandel group annotated for German and Hindi and English, like a hierarchical classification. We have just annotated as a classification problem. We consider as a binary classification problem. We annotated as whether the content is hate speech or not. So as I said, here our coverage is Malayalam and Tamil, the main two Dravidian languages. This is the task description. So in our two different tasks. So as I said that one of our aim is to cover different kind of code mixing. The first task deals with about the native script, also as well as the Latin script. Native script as well as native script in the first task. Second task, we purely concentrate on the cross script, cross code mixed. It means that only the Latin script. We are not finding any native script. It means that in our data set of the task, collected from the YouTube comments, we collected from the tweets and then other social media applications. So this is regarding the first task. So I would like to see how it's different from the why we have the task. Task two, as I said, that task one is the script itself. So we are finding the text in Malayalam scripts, and we can find a script, and we can find the content in a Latin script also. So that we are considering here, it's a code mixing. So one type of mixing. So, and as I said, that we collect YouTube comments. So we used the tool YouTube comment scraper. Using that, we have we have extracted the YouTube comments. So it's regarding that task two, Tamil and Malayalam. I said that here the comments or post will be on post or only in the Latin characters, Latin or Roman characters. So we have concentrate only on that cross coding here. So in the Malayalam, we have collected from the YouTube, but interestingly, what we did for Tamil is actually we collected from the Twitter. So using we use the API, even though it have some limitations. So we have collected around 3,000 from the Twitter, and we have collected from the other app. Now it's banned actually, Hello app, where we found that there are a lot of people are posting their comments in the Hello app. It was one of the famous app before COVID. So we have manually collected from the Hello app. We have collected I mean, there is no option for API because it's app. We have manually collected the a post, and then with the help of 2 experts annotated with whether it's a hate or non-hate. So we haven't gone for the inter-annotated agreement. So in our procedure, we followed a different way. The first will be that the annotation by the PhD scholar, that will be the language expert. So like that, we just annotated hierarchically. Okay, this is our data set details. So you can see that. So in order to maintain the consistency, we just stick on to that 5,000 in the task 2, 5,000 post and comment, 5,000 in task 1. Out of 4,000 in training data, we used in a task 1 for Malayalam 3,600 total training data. So 400 we released separately for the development set, and testing 400. In task 2, hello. Okay. In task 2, Malayalam, you can see that the 4,000 training data were used and 1,000 testing data. In 4,000 comments, 1,953 are offensive and then 2,047 are non-offensive. So it's a balanced data. Particularly the task 2 is a highly balanced one. In testing also, you can see that 512 and then 88. The Tamil task also the same way. So 1980 offensive in the training and 2020 in non-offensive. So as I said earlier, we haven't gone for the fine-grained classification. So we just we started doing this. In the next fire, we'll come up with a fine-grained classification like the German languages, what Thomas presented. Fine. Another interesting thing is the Tamil 4,000 out of 4,000 training data. So around 3,000 we have collected from the Twitter and 1,000 from the app, Hello app. So this we have collected with the help of students. We have collected. We asked them to manually collected means from mobile phones. We have collected from mobile phones, and people copy the post and then pasted in a document. Then later we cleaned and then we annotated. Okay, these are the this is just an overview about the participants. I think yeah. So totally around the registration was little more. We received near 100 registration, but the final submission up to paper is, we can see that around 12 teams only participated in the task 1 and 13 in a task 2 and then 13 in a task 1, I guess. Task 2, yeah. 12 in task 1, 13 in task 2 Malayalam, and 12 in task 2 Malayalam. Okay, these are the widely used systems what they have come across. I just made it as a 3-part, pre-processing, features, and classifiers. When you're seeing the pre-processing as teams, very few teams only use the teams remove the hashtags and then special tags and emoji, the usual pre-processing. And we come across that some teams are interestingly doing that. They try to translate and then transliterate the content. So as I said that the content is completely code mixed, so they transliterated using their existing sources and after the feature extraction and classification. That's a notable in a pre-processing. In the feature side, so the usual character engram and TF-IDF features, we have seen that from the quite a few systems, character engrams and TF-IDF, we have seen that. And then as few teams, a subbird representation model. Subbird representation modeling, and as you know that the transformer, so people tried the transformers, multilingual boat and Elmo model, and Roboto also people tried, and a team actually tried that ULM fit. They just it is synthetically they generated the code mix data. As you have seen that the data set what we are using is only the 4,000. In order to increase the coverage, so they synthetically generated in order to use the transformers using ULM. Unfortunately, they haven't reached the first place. They got the reasonable. When you're coming to the classifier side, the usual traditional starting from SVM, because we allowed 3 submissions and then we choose the best of 3. So people tried with the logistic regression, SVM, and then all the basic classifiers. And interestingly, a few deep learning classifiers, also combination of convolution networks as the BiLSTM model. And the team tried the Roboto with the XLM classifier. And one thing, the whom I think the team, I forgot the team name. I think they tried the self-attention based BiLSTM model. Yeah, who worked on the subword representatives. So they have tried the class of different attention based classifier. They are the only team who worked on the self-attention based classifier with BiLSTM. Okay, when you come into the discussion about the, I said that 12 submissions for the task 1 and 30 for task 2 Malayalam and 12 for task 2 Tamil. And model, we can see that we can. I feel that the thing will become a the problem statement. Okay, so it's regarding the second place. IIT Bombay CFILT from IIT Bombay and then the SSN team. So they received the they achieved the second place of 0.94 with a small difference. And when you come to the task 2, the same language. So here you can see the interesting difference actually, even though the data set size is similar, because of the cross code mixed script, the Malayalam is and then the linguistic nature of a Malayalam language, and then because of that a lot of ambiguities in that code mixing script. So the first question is first place is only 0.78. And then second is actually 0.77. First is from bits and then second is from KBC. So when you come to that Tamil task 2, again the bits team reached the first place with the 0.9, and then they have used the transformer model. And second place achieved by the SSN. So they tried the conventional model TF-ID of, and then they got a 0.88 F1 score. So this is the overall results of the team actually. So here we just listed out the precision and recall, and then we made the rank also. Task 1 Malayalam, so the result was a little closer. So you can see that near 6 to 7 teams or 8 teams are there above 90%. When you come to the second cross script based model, the task 2, subtask 2. So here the accuracy starts, or the maximum accuracy 78 F1 score, and you can see the difference here. So the ranges, but people are, up to top teams are a little closer, 0.77 and 0.78. So when you the Tamil, so as I said that the bits team who a transformer based model place 0.9, and then the SSN team they're the second place. So others are also in the same range like how we have seen in the task 1 Malayalam. So the accuracy is above 80%. So baseline also we have baseline we tried actually. It's a baseline with 0.84 with the TF-ID of word features with SVM. So when you come to the conclusion, so I would say that it's a good experience for us to organizing the subtrack. It's under the one, the well-known one hazard. So here, as I said, that we concentrated only on the coarse grained one. So only the 2 things, binary classification. So in future, we thought of adding more Dravidian languages, as well as to making based on the type of hate speech, or whether it's a targeted to individual or group. So that we are working on it. So this, as far as we know, that it's a first data set for Dravidian languages. So as we know that it's a under-resourced language with a code mixed content. So interestingly, models performed well for a few systems, few tasks, and then equally the conventional models also with the TF-IDF features also I think performed well. So this we are having a look onto it, and because people haven't tried any specific dictionary, or that's what we are thinking. We thought of developing a system with a hate specific any dictionary based, or extracting the or taking data information from the openly available from the training data. So that interesting thing in the participation side. So hope we are expecting that in the next year. So that's all from my side. So these are the references. So once again, I thank to Bharati and Thomas Mandel and the whole FIRE team for making this task successful. I would like to have questions. Any questions from the participants? Hello. Any questions? Any questions from? Okay.
Okay, I think yeah we can move.
Yeah, sure. Thank you.
Yep. Thank you, Anand. Yep. Okay. So the next presentation is on sentiment analysis of Dravidian languages in code mixed text by Bharti Raja Ashoka Chakravarti.
Hi. Good evening. So our talk is a sentiment analysis for Dravidian languages in code mixed. So I'm Bharti Raja Chakravarti, and this track was organized with the help of many people like Vignesh from Cardiff University and Ruba Priyadarshini from the Madurai College, Madurai Kamaraj University, and also Charlie from Trivulatium, Kerala, and John McRae and Shardal Shuran team, including me. I'm from the National University of Ireland, Galway, and Navya Jose is also from Trivulatium, Kerala. Sorry. So our track is the sentiment analysis of Dravidian languages. It's more on this. So sentiment analysis is a growing area, but the problem with the social media content is the code mixing, as previously Anand was explaining. And also it's not many research has been done on the Dravidian languages, which is kind of like under-researched languages. So for people who are new to Dravidian languages, so this is a Indian subcontinent. So there are four different family of Dravidian languages are there: South Central and North group and Central group. So Tamil and Malayalam falls in the South Central group, and Kannada also falls in the South Central group. So Telugu, and including these four languages, these are the four literary languages. But there are many, like nearly 40 Dravidian languages are there, including Tulu and Bukhari in Pakistan area. So these are the Dravidian languages. We won't discuss whether it's whether the Aryan invasion is historically true or not, but linguistically we are agreeing that the Dravidian languages are different from the Indo-Aryan languages. So coming to our task, where the main part is the code mixing. So this phenomena is usually happens in multilingual country, and this is a mixing of words, morphemes, or phrases between two or more languages when in a speech or in a writing. So this was not this was happening for a long time, but this was not in the more study in the past, due to the fact that if you write code mixed text, that's not considered as a proper language, so that is frowned upon. So most of the formal texts you won't see code mixing, but because of the social media and then the hype of the internet, people started writing in the code mix. It's because people started writing how they feel. But I guess another problem was people started writing in the non-native scripts. That's a Roman script. So as you can see here, Tamil has its own script and Malayalam also has its own script. And the Tamil scripts evolved from the Tamili and then the Vattarathu and Chola Pallava scripts. And Malayalam also evolved from the Chola, Vattarathu. And so even though they have its own script, but they are all using, most of the users in social media are using the Roman scripts because of the availability of the keyboard and it was easy for them to do it. So we collected the corpora for this, and then we are doing our task is about this. So here you can see this in the first sentence, all the words, all the blue words, it's all Tamil words, but they are all written in non-native scripts, Roman script. So the translation of is given as after the movie release, everybody will celebrate the hero. And there is another kind of code switching, which is a tag switching. So at the and as well as the intersentential and intrasentential switching also happens in this. So the motivation is, as it's a low resource language, but compared to the population of the Dravidian speakers in India itself, it's very big. But there is not many research resources are available for this, and most of the research in NLP community are moving towards in English. So we thought, okay, this would be an interesting one, and this is also real-time applications. So we created this task by annotating the YouTube comments as a positive, negative, neutral, mixed emotion, or not in the targeted language. So this class comes in here because even though we use the language identifier to discard the comments which are not in the required language, but sometimes we got these other language text because of the routed in Roman script or some other things. We are not sure why we are getting this. So after the pre-processing, and then we gave it to the annotators to annotate. So the whole process of the data collection for this process is we collected the YouTube comments from the YouTube. So we used YouTube comment scraper. So to collect this, we chose movie trailers from Tamil and Malayalam, and we tried to collect the movie trailers from 2019 and 2020. And then from there, and then we collected the data, and then the unprocessed data was then pre-processed to remove the not intended language and some of the things, which is if the comment or sentence has only emotions or which doesn't have text. So we discarded those sentences. After pre-processing the data, we created a Google Forms, and with the Google Forms we sent out to the annotators, and each sentence was annotated by minimum 3 annotators. After the annotation is done, and then we try to find the majority of it. If there was no majority after the 3 annotators, then those comments are again sent to another 3 annotators. These are the not same annotator, they are different 3 annotators. After that, we got the majority of it. If we didn't get the majority after all these annotation, we discarded those sentences. We will look at the sentences for different purposes, but for this task we discarded them. And after that, we had the code mixing corpora, which was released for this. And the data set has for Tamil English and Malayalam English. So we have the total number of sentences, comments were 17,000. And for the Malayalam was 7,000. And we used the 60 and then usual splitting for the train development and tested and released them. And for the inter-annotator agreement for the Malayalam, we got Griffin's alpha of 0.9. So because we used Griffin's alpha because not each sentence is annotated by all the 3 annotators because of the way we did the annotation process. So Griffin's alpha was the correct process. The Cohen's kappa and the other annotations, inter-annotator agreement metrics require the sentence has to be annotated by all the annotators involved in the process. But Griffin's alpha doesn't need that kind of strict regulation. So, and after this, we got this. And for Tamil, we got 0.65 for Griffin's alpha. and the data set is also kind of like highly imbalanced. So you can see this you have like a more positive compared to neutral state or negative. So the main reason behind this is people who come for who go look at the trailers of the movie, they usually go the fans of the actors or actresses, they go and search for the movie and then they watch it. Only those people. So most of them, when they comment also, they comment positively. And we got very less negative comments, and we have mixed feelings and neutral states. And when they start comparing two or more movies, and then we put them also in the mixed feelings. And we have the other language class, which is not in the class one. So we received nearly more than 100 participants register for the tasks for both Tamil and Malayalam. But the final submissions, we received 32 submissions for Tamil and 28 submissions for Malayalam. And the top ranking methodology from SRJ team, they use the XLM Roberta of the output of the top hidden layers in XLM Roberta, and used for extract the information and then fed them them as an input to CNN and concatenated to get the better results. And for the other team, the second ranking team, they use the embed. And so this is kind of like we saw most of the models that was used to do for Tamil and Malayalam. They all have a similar kind of like using BERT and Roberta and these word models. Only very few participants use the old traditional machine learning algorithms. But before that, we also did the machine learning algorithms. And for us, the baseline we set up was like 0.6 for F1 and precision and recall. And so for the evaluation of the tasks, so for the test set, for the Tamil, we sent out 3,149 sentences. And for Malayalam, it was 1,348 samples. And we used the weighted average F1 score. So for the precision also, we calculated it with that was weighted average precision and recall. Because of the class imbalance, we used choices. And so we asked this to participants to submit above the baselines, but two participants who submitted the results, we found out that their results was below baseline, even though they used the BERT models. And one of the participants from Balasundar from the research from Bangalore, in his research they have used the sound text. So that was a very innovative idea to use it. And other than that, most of the participants use the BERT flavors of BERT. So yes, this the results. So this precision recall and F1 score are weighted average precision recall and weighted average F1 score. So out of 119 participants, 32 final results were submitted for Tamil, 28 for Malayalam. And as you can see from the figure from the top 10 submissions for Tamil track, so the recall was high in almost our systems, and the systems did not perform above our baseline. Not like our baseline was 0.6, and they are like performed little better than that, and they couldn't achieve more than this. So, and also with the Malayalam, our baseline was it was also 0.6, yeah, 0.6 nearly, but the performance by the system participants were like high. Even the top ranking system SRJ, that was the rank first in both Tamil and Malayalam, they didn't reach 0.8 in all the precision and recall. So this is due to the fact that we believe that this is a code mixing, and this is and also the low resource settings also makes it even more difficult for them. And there were no libraries to be used. There are not like libraries like CentiWordNets. Those are not available for this code mixed text at this level, and written in non-native script. And also when it was written in non-native script, there is no standard form of for spelling. So everybody writes in their own phonetic transcriptions. And then the another problem, we think it might be the class imbalance problem. So it's because one positive classes has the more data than the other classes. Finally, the thing out of this chat, as we concluded that this is like this is a very good case study for unbalanced data set, and also as a code mixed and Dravidian language text. And both we found out both the traditional machine learning as well as the deep learning models were used. And for the next year, we plan to do for the other Dravidian languages, Kannada, Telugu, and Tulu also. So, and also we plan to we have the mixed script as problem as well. And that's the end of the talk. If you have any questions, you can ask me. Thank you.
Okay, any questions from the audience? All right. Okay, so we will take a break here for 10 minutes again, and then we will continue with our track overview presentations. Thank you. Okay, hello everyone. Yeah, we are back again. So next presentation is on retrieval from conversational dialogues, presented by Devasis Ganguly and Pruchita Singh.
Hi, is my screen visible?
Yeah.
Okay. Okay, so this is a presentation of the TREC Retrieval from Conversational Dialogues, or RCD, in 2020 FIRE. So it's going to be presented by me and Pruchita. So this has been a collaboration with Dublin City University, Ireland, and Indian States Institute. Deepasri comes from there, and Manisha Verma from Verizon Research. So this will be presented by myself and Pruchita. Okay, so I wanted to give you a background about this task. So basically, if you think about traditional information retrieval system, basically given a query, you need to retrieve a ranked list of documents. So that's the standard IR. Now, moving from that paradigm in conversational search systems, what we aim to achieve is something quite different. So we assume that the user is not aware fully of the information needs, so he doesn't need, or he doesn't know how to formulate the query in precise terms. So he wants to interact with an agent. That agent could be a conversational agent which speaks with or communicates with the user. And then lets him and then asks clarifying questions, so that the objective of the agent is to get to know the user better, or get to know the information need of the user better. So just to give an example, so this is particularly applicable in customer care situations. Like, if you want to troubleshoot something, let's say, your Mac is not starting, or the display of your Mac is not working. So, I could be calling, a customer agent, and then could be letting that person know that, my Mac screen display is not working. And in that case, what the agent could do, in that case, the human, he could be asking more clarifying questions like, did you try to restart your Mac, and did you try the hard restart of your Mac? Did you try to flush out, something from memory, the NRAM of your Mac? So, his objective is to try to boil down, or try to delve into the more specific details of the problem itself, so that he could be giving you a more relevant information about that particular information need that you are having. So the holy grail of the conversational IR is to replace that human, with an automated agent, who could be asking clarifying questions in order to be, in order to trying to know the information need of the user in a better way, so that it could serve more relevant documents to him or her. So our work is not about that notion of conversational IR. Our work is a bit different, because given a conversation, we would want to contextualize the conversation itself. So I will in the next slide, I will show that with an example. So imagine a situation, where I am communicating with a friend of mine through a chat service. So let's say, for example, I type in the word like, I absolutely loved dark. Now, if my friend hasn't watched the Netflix series at all, it's quite difficult for him or her to understand, what am I talking about? So this is something. So in that case, he has, or my friend has to ask me a clarifying question that, what do you even mean by that sentence of yours? So that will mean that he has to ask that question, and often he won't ask that question, and then I don't know. So this could cause a gap in the communication between me and my friend. So what might happen is that if an intelligent agent is sitting on the server side of such a communication program, and then if it has access to my profile and my friend's profile, and then it could possibly know that my friend is not into fiction, is not into TV series or fictional TV series at all. Maybe he's into documentaries. So if it has that information, then it's possible for that agent to know that probably it's difficult for my friend to make sense of this particular sentence. And in that case, it might be helpful to provide some additional context to my friend. So this part of the screen on the right side that I'm showing, it won't be visible to me. So the left part is something that I see. So I'm not aware that there is an agent sitting behind. who could be providing some more context to my friend or to the party to which I'm communicating to, depending on the need. So in that case, it makes sense that if this small info box is attached to the screen that my friend is viewing, it's possibly helpful for him because it tells it contextualizes my my sentence or what I have told to my friend. It contextualizes the fact that what I meant, and then it's easy for my friend to make sense of what I said without me being aware of it, without me being aware that there is an intelligent agent who is sitting at the back and then trying to provide this contextualization to my friend. And similarly, even to me, if I'm not able to make sense of something, then probably the agent will find that and then provide relevant information to my screen as well. So this is roughly the use case that we are targeting. Now, to answer this research question, so to answer this research question, so we need to be kind of building a data set so that we can conduct research at the laboratory, and we can try to see what methods are effective for this particular task, what are the models that we should be using, what is the pipeline, what are the different components of a system that we need to kind of address, and what are the research questions that need to be investigated for this kind of use case, or for this kind of a system, for this kind of a system. So in that case, so the objective of this particular track is the automatic contextualization of two-party or multi-party dialogue systems, right? Now, for this example of the chats, and although this system could be useful in a chat scenario, but to get real-world chats, it's a problem, because there are privacy issues, and then it may not be possible to get access to what people usually chat about, because that could mean that there could be privacy breaches, and it could be difficult to get access to those data sets and compile those data sets. So what we could do is, so we thought about replacing the chat dialogues with dialogues from movies, because they are scripted dialogues, and there's nothing to, there won't be any privacy breach if we release that as a part of the data set to the participants or to the research community. So people would be contextual, or people will be researchers will be trying to contextualize dialogue acts from movie scripts without any problem, because there won't be any privacy breaches if we release that data set. So that was one of the motivations why we moved on to movie dialogues. So the task is and then we wanted to focus on movies where there will be people communicating, and then there will be people communicating a lot. So there will be we don't be something like so in movies, so you could have long sequences where there is no communication between the actors, but then that won't be suitable for our situation, right? So if in our case, we'd want the actors to speak a lot, because only then it'll be able to make sense of contextualizing what they're saying. So we compiled, or we came up with a list of movies that are heavy dialogue based, that there are many dialogues spoken between the main actors in the movies. And then, so that's something. So while formulating the queries in our data set, we kept this in mind, that we wanted to compile data sets from movies, where, there are many interactions between the dialogues, or between the actors. So the task itself is so given a long context, you'd want to find information from that context. I'll cite that with an example in my next slide. So this is an example taken from the movie 12 Angry Men. So if you can remember, that movie has got lots of dialogues between the actors, right? So this is one particular example, where number 2, so it's a communication between two jury members, number 2 and number 8 to be precise. So number 2 is saying that he's guilty, and I thought it was obvious. I mean, nobody proved otherwise. And number 8 is saying it's on the prosecution. The defendant doesn't have to open his mouth. That's in the Constitution, the 5th Amendment. Now the thing is, in this case, so imagine that two people are communicating, and then just like the example of the chat that I had shown. In this case, when number 8 is talking about the Fifth Amendment, it may be the case that number 2 is not aware of that, right? So it could actually help for number 2, if you can provide some more information about the Fifth Amendment. So he doesn't need to look up the Wikipedia. So imagine that, if it's a chat server, then I could look up that information myself, but maybe I'm too lazy, sometimes, and I don't want to look that up. Maybe, I will ask that question directly to number 8, what do you mean by Fifth Amendment? And then, it could be, we could waste both of our times, right? When number 8 has to explain that what that is. So this is a situation, where our system or, research in this direction can really help. Because, in this case, you'd want to find documents that are relevant to this Fifth Amendment. So that's the overall, this purpose of our TREC, or the motivation of the TREC. And I will leave the floor on to Pachata now, who will be explaining the rest of the TREC. So I'll leave the floor to Pachata.
Can you see my screen?
Yeah, it's visible.
Okay. So there are two tasks in the RCD's track specifically. The task 1 was about extracting the spans of text representing potential information needs requiring to be contextualized from a dialogue context. So a dialogue context was given, and the participants had to extract the spans of text representing the information needs. And the second task was about retrieving potentially relevant passages from Wikipedia that will help to satisfy the information needs extracted from the dialogue context. So we provided two different text collections. So one is the the text collection from where the participants had to retrieve the passages, and the other one was the topic. So for the text collection, we released the Wikipedia collection. It was a dump from 2019. And there were we marked the passages of the Wikipedia collection with the p tags, and along with the XML file, we also provided them with a text dump where we had the delimited separated text file comprised of the text extracted from each passage of the Wikipedia articles along with the passage identifiers. In terms of topic, so we used we basically annotated 4 movie scripts, namely Pi, 12 Angry Men, Good Will Hunting, and The Name of the Rose. We manually annotated the text spans that were likely indicators of potential information need requiring contextualization. So for task 1, we automatically constructed a dialogue context by selecting a total of 5 sentences preceding and succeeding from each annotated text span. Context size 5 indicates a reasonable compromise between too short and too long contexts. Each topic was represented in TREC format, so they had a unique topic ID, and the title field was the manually annotated text span, and the description field was the context that I described that consists of 5 sentences preceding and succeeding the annotated text span. So we did the relevance assessment in 2 phases. The first phase was pre-submission phase relevance assessment. So there, for each topic, we constructed a pool of passages by a combination of number of standard retrieval models, for example, BM25 language model. With each retrieval model, we obtained 2 different rank lists of Wikipedia passages, one with the title field only, and the other with both the title and the description fields of the topic. And then we employed a depth 20 pooling on the retrieval results to obtain an initial set of relevance judgment at a binary level of granularity. Then after we got the run submissions from the participants, we constructed a new depth 20 pool by combining the submitted runs. And we conducted a relevance assessment on the new documents that we collected from the submitted runs. So we used 2 different categories of evaluation metrics. The first one was for the task 1 evaluation. So in task 1, we need to measure the quality of an automatically extracted fragment of text with the ground truth of reference, which is the title field of the topic. Now to measure the overlap between these automatically extracted text and the ground truth, we used character level overlap measure and word level overlap measure. So character n-gram level overlap measure. So to measure the character overlap, we used weighted character n-gram based BLEU score. And in this BLEU score, we gave higher weights to the higher values of n. That means like if more, I mean 5-gram character overlap will be given more importance compared to the 3-gram overlap. So in this way, we computed this weighted n-gram based character n-gram based BLEU score. And for word to measure the word level overlap, we computed Jaccard score. For task 2 evaluation, in task 2, we basically need to evaluate the effectiveness of the retrieved passages from the Wikipedia collection. So we used precision at top 5, mean reciprocal rank, and map, which is mean average precision, as our evaluation metrics. This is the result that we got. One team from Dublin City University participated in this track. So they submitted 5 brands. So in general, observation from this table is that a method that is better able to construct the queries, which performs better in task 1, also leads to better retrieval results. So for the participating team, the summarization technique with KL divergence performed best for both task 1 and task 2. So as a conclusion, I would like to say that the datasets and tools that we released as a part of organizing this track would be useful to the research community for carrying out reproducible research on topics related to conversational search agents. So in 2021, we are organizing a workshop in Wisdom, which is just an extension of this track. And we will also like to continue organizing tracks on this subsequent versions of this track, and we also aim to extend the dataset and propose other novel tasks related to conversational search assistant. That's what from my end. Thank you.
Okay, any questions from the audience? All right. Thank you, Devashish and Kochatan.
Thank you.
We now next we move to the next presentation. The next presentation is on fake news detection in the Urdu language, presented by Mas Amjad.
Hello, do you hear me?
Yes, Mas, I can hear you.
Okay, so I'm just like going to share my screen.
Yeah.
So do you see my screen now?
Yeah, your screen is visible.
Okay. Okay. So first of all, thank you very much for organizing FIRE organizing committee. It was indeed an amazing opportunity to organize this task. So in the presentation, I'll be talking about the overall overview of our task and like the contributions and everything. So please bear with me. So the title of my presentation is overview of the shared task. So I'm just going to minimize that so you can see that clearly. Okay. So and we collaborated. So and we are in Mexico City. So the institution name is Centro de Investigación de Computación in Mexico City, and this is a research center in a university called Instituto Politécnico Nacional. The name is in Spanish. We collaborated with a well-known researcher called Paulo Rosso, and he works in a University Politécnico de Valencia in Spain. So the task organizers were from United States, from Mexico City, and from Spain. So my presentation, I will just give you a the table of contents. So in the presentation, I'll be talking about what was a key motivation of this task, and like how many participants they participated in this overview, in this competition, and then how we collected the data set, how we annotated the data set. I will be talking about that. And then I'll be talking about machine learning classifiers, and I will conclude this presentation by highlighting the contributions and then like the results. So to begin with, so I would like to define the definition of fake news. So fake news is a news article that is like intentionally and verifiably false. So we have an event, and the event has passed, and now we have a news, and that news talks differently and presents different factual information that indeed the truth, no truth. So and why this is a problem? Because fake news is amazingly affecting our society, because many media, news channels, many press, they are manipulating this. So, and why they are manipulating this? Because they can have different financial cause. Some people, they use fake news for propaganda to harm someone's personality, and sometimes it is used for political objectives. So this is why fake news is a real problem, and it is very important to address this problem through automatic ways. So if we talk about financial terms, so you see like this picture shows why and how fake news can really affect a stock market. So for example, within a matter of minutes, so we can see like the stock market just like collapse, and then again like manage to stabilize the stock market. So I think this is very important to understand. A tweet which can be a fake can really harm a stock market as well. So that also indicates that a fake news is a genuine problem, and we really need to devote some efforts, some scientific contributions to address this problem. And now, so the fake news is one problem, and the second problem is we are generating a huge amount of text each second, and processing that text is also another substantial task. So this is why there are two tasks. One is processing a big amount of text, and in the meantime introducing new machine learning models, new methods to combat fake news. So this is why this was also the main motivation to address this problem. And why we focus on low resource language such as Urdu, because in English there is a huge community, who is working on fake news detection in English language. So, but no one has worked before in Urdu language. So there are more than 100 million speakers in Urdu language, and this is why it is very important to devote some research to contribute in this domain, so we can also develop some NLP tools for the Urdu language. So this is why this was one of the many motivations to address this task, especially in Urdu language. So now I'll be talking about the demographics, how many participants we had, and how many people they participated from different countries. So if we talk about participants, so 42 teams they participated in this competition, and we had only 9 teams. They submitted their experimental results, they presented their code, and they also presented their results. So if we talk about the participants, so we also see that huge people, many people they participated from India. For example, we have like this SSN college, then we have IIT, then we have IIT Patna. In the meantime, we also received many participants from Pakistan, for example, UMT, Then we also have this like NUEDU.park. Then we have academic university. So we have like a very diverse participant from different countries. So if we talk about who were there, so we can see that more than 70% the participants were students. We had 10% faculty, so like 23% faculty members, and we had more than 4% research scholars who participated in this task. And if we talk about the countries, so we can say that 15 out of 42 participating teams were from Pakistan, 22 participant teams were from India. We had one team from Egypt and one team from England. We also had a team from Germany and 2 teams from China. So overall, we had 6 countries, participants from 6 countries, and it was very important for us because we introduced this task for the first time, and we are very happy that we had a good number of participants who participated in this task. So now I'll be talking about the data collection and annotation procedure. So as mentioned before, like we have many resources available for the English language, and we do not have such resources for Urdu in the form of NLP tools. Then like a large scientific community is available for the English language, and we have a very small scientific community for Urdu language. The third most important point is data. So we have a huge amount of raw data in text in Urdu. On the other hand, we have a very organized and annotated data available in English language. So I think this is why it is very important to work on low resource languages. And this is why in this task, we primarily focus on Urdu language. And if we talk about what are the available tools for verification, so we know that there are some websites, there are some services which are available for English language. For example, Snopes, we have PolitiFact. So these are the websites who perform fact checking in English language. On the other hand, we do not have any services for Urdu language, and most of the text verification task is done by manual process. So this is why it is also important to address this challenge. It would be also nice to present some verification tool for the Urdu language. So now I will say how we collected the data set. So first we collected news for 5 types. So our data set has news in 5 domains. So we have business news, health news, showbiz, sports, and technology. And we used multiple sources, national and international. For example, we use sources from England, from United States, from India, and other news channels. And so we collected real news from these news sources, and then we annotated them manually. On the other hand, when we wanted to collect fake news, it is a very difficult task to find a corresponding fake news of the real news. And this is why we use a crowdsourcing. We hire some professional journalists, and we asked them to write fake news for us. So our data set, so initially we have published a paper, and in that paper we presented a data set in which we had 900 total news. But we, for this task, we augment that data set. So we increased the number of news for this competition. So originally we had 400 fake news and 500 real news, and we published this paper. And for this task, so we used that previous data set as a training data set. And for the testing phase, we introduced a new data set which had 250 real news and which had only 150 fake news. So in total, the data set contained 1,300 news. So that's why we just like separated into 2 data sets. So training data set, first we release training data set, and we ask our participants to train their machine learning classifiers. And then to test their performance, we release a testing data set which contained 400 news, and then we receive their performance on the testing data set. I will also talking about the performance in the subsequent slides. So if I talk about more specific channels, we collected the news. So we use BBC Urdu, we use CNN Urdu, we use Express News from Pakistan. So, and initially we collected 15,000 news articles in 5 domains. And after a very rigorous annotation procedure, we ended up only having 750 real news articles. So in the annotation process, we had 10 annotators, and we just like clean the data also. So for example, for the annotation process in the real news, we verify whether each news present other sources. So if there is a news, let's say published in BBC News, can we find the same news in CNN? Or can we find the same news in Express News or other news channels? And then we also verified whether the title and the content of the news match, because sometime we also encountered some news, the title says topic A, but the content was a different topic. So this is why it was also very important to verify whether there is a relation between title and the content of the news. The third most important point, we also match the date and the place of the event. For example, sometimes some news channels, they publish a news with a different date and also with a different place of the event. So this is why we used these criteria as filters while we were tagging our news articles as real news articles, I'm sorry. And for the fake news part, since I mentioned it is very difficult to collect fake news from wild, and there are no available fact-checking tools for Urdu language, and defining a very rigorous criteria for fake news is also not clear. So this is why we use crowdsourcing, and we hire some professional journalists to write fake news for us. So we provided them real news, and they wrote fake news corresponding to that real news. So we did not provide them a very detailed restrictions, because we thought that could harm the fake news process. So this is why we just requested them, please maintain the number of words and the news length. For example, normally BBC News contained more than 1,500 words. So we ask our journalists to write at least 1,500 words while they are writing fake news corresponding to that news. And we just provided them real news, and then in the end they provided us back only the fake news. And in the end, we had a very limited budget, because crowdsourcing require a substantial amount of money, and this is why, due to the budget limitations, we had only 550 fake news articles. And now, if I talk about data statistics, so in the training data set, which we published before, and the paper is available online. So in that data set, we had 900 total news. So each category contained 100 real news, and business and sports contained only 50 news, and the other had only 100. So in total, we had 500 real news and 400 fake news. On the other hand, for this task, we presented a new data set for the testing phase, and each domain has, in the real news section, each domain contained 50 news article. And for the fake, once again, for the budget limitations, we had managed to collect only 30 fake news. So we asked our professional journalists, we provided them 50 news articles, and then we asked them to choose any 30 news and then write fake news corresponding to that news articles. So in the end, we collected 250 news for the testing data set and for the real fake news corresponding to the real news in the testing dataset, we had only 150 news. So this is the real example of our dataset. So for example, this is the dataset. This is a sample from our dataset used for this testing phase. So we have this news that corresponds to the sports category. So in this news, it says Virat Kohli, who is a cricket, who is a cricketer, and he's the second the richest person in India. And the fake news was he is the poorest guy in the Indian history. And if we also talk about, and we also like presented that both news in English. So if there is a non-Urdu speaker who cannot read Urdu, so they can understand by looking at the translation. So we see that like there is a very small difference in the news. For example, here in this real news, the news mentioned like Virat Kohli, who is a cricketer. He is the second richest person in India. On the other hand, the fake news says, no, he is not the second richest person, but he is the poorest guy in the whole cricketer team. So he is a very poor guy, and he is the poorest cricketer among all the captains in the Indian history. So we see that like even tweeting small words can really change the meaning. For example, here he is the second richest guy, and here we say no, he is not the second richest guy, but he is the poorest guy among all the previous Indian cricketers. So this is very important. So we see that like we also we can observe like there is not much difference in the news, but even if changing small like words can really change the entire news. So this is was only the one example that we choose, so we can really show like how the samples in our data sets look like. So if we talk about now machine learning classifiers, so first we say that many people, they have been working on different languages. For example, English, Spanish, they use different features such as n-grams, they use parts of speech tags. On the other hand, if we talk about Urdu language, so primarily many researchers, they use n-gram combinations, and because like there are not many parts of speech synthetic features, and this is why finding what are the best features is also a difficult task. So this is why in this research, initial research, when we presented our research paper in the form of data set, we used only n-gram combinations, but we use different n-grams. So if we talk about the approaches used in this computation, so different teams use machine learning classifiers, which we may call as non-neural networks classifiers or non-neural network approaches. So some teams, they use SVM, some teams use decision tree, random forest. On the other hand, some teams also use both. They use non-neural networks approaches and also neural networks approaches. So some teams use word embeddings and also neural networks, and some teams also use transformer-based approaches such as BERT. So this is the technical report. So this is the overall view of the team. So we received nine submissions from different participant teams, and only 6 teams, they presented a technical report. And this is why this is like a very brief overview. So for example, the team BERT Forever, they used a context embedding BERT, and they use character convolutional neural networks, Roberta, and then they received more than 90% results. So on the other hand, if we see the least results, so we see this team, SSNCSENLP, they use simple features like vector n-grams, and they used different weighting schemes. For example, for the simple machine learning, they use TF-IDF, and then for the deep learning they also use fast text and word-to-vec embeddings. And they also use like AdaBoost for machine learning. They also use SVM and random forest. And for the deep learning, they use multi-perceptron like there. So in overall, so we had different, our teams, they use different approaches, and but overall the best results was obtained by team Bird Forever. So I will also mention, like, highlight how they obtain their results. So to evaluate the performance of machine learning classifier, we used two different approaches. So one way was detecting fake news, and which we call as a F1 real, and the second one was F1 fake. So we calculated detecting, so F1 real was like detecting real news out of all news, and in that case the true positive was the number of correctly detecting real news. For the F1 fake, we use this metric as a true positive, so the number of correctly detecting fake news. We also use accuracy, although our data set was not balanced, but we just use also accuracy, and we use F1 macro. So F1 macro computes the F1 score for each class, and then it takes the average to calculate F1 macro overall for the overall data set. And then this is the summary of our results. So we also presented a baseline. So first we presented a random baseline, so which was not that really bad. So here we have 49% F1 macro, and then we also presented a baseline, traditional baseline bag of words, and here we got 78%. And the third baseline we presented received 88% F1 macro. And the best team, which outperformed all the other classifiers, was from China. So they got more than 90% F1 real. And if we talk about F1 fake, so they got 87% F1 fake. So overall, their system obtained 90% F1 macro and 90% accuracy. So if we talk about the least performing classifier, received only 49% F1 macro, which was even lower than the random baseline. So if I conclude my presentation, so what were the contributions? So first of all, it is very important to address fake news detection problem, especially for low resource languages such as Urdu language. And we contributed by introducing a first data set in Urdu language. This data set contained 750 real news and 550 fake news articles. We also introduced a baseline in the first research paper, and then we introduced this task at FIRE. And then in this competition, many participant teams, they presented their different classifiers. So if someone would like to contribute by augmenting the dataset size or by checking different machine learning approaches, I mean, they're more welcome. So if someone wants to use datasets, so dataset is publicly available. So dataset can be easily downloadable by this link. So now I will switch to future work. In the future, we are planning to use different techniques to perform fake news detection tasks. For example, we would like to remove name entities and check whether a machine learning algorithm can predict and can differentiate a new fake news and real news. We will also would like to translate this complete dataset into English language and then use the same baselines and other methods and verify whether those methods perform the same or they perform better or poor results. So these are the future directions that we would like to investigate in our future research. And then we will also would like to investigate fake news problem in 2 different ways, as deception detection and also rumor detection. So now I would like to ask if any questions, then I would like to address them.
Can I ask one quick question, Maz?
Yeah, please.
So you showed an example. It's kind of an interesting example because the fake news that you showed, so a part of that was true, in fact, because the income about Salman Khan and the income about Dhoni, that was true. But the part about Virat Kohli was false, right? Could that be an interesting case? I think a more interesting case could be trying to, predict the falsity from a news, that the entire news may not be fake, but a part of that could be fake, right? So detecting that part precisely, could be a more challenging research question. What are your thoughts on that?
Exactly. So you see, like, so that also deals with text summarization technique. So imagine we have a news article. So I think this news contain approximately 200 to 300 words. And if we talk about overall news, finding a very specific part, for example, here only few words talk about, okay, so he is a second richest guy, and here says no, he is not a second richest guy. That is the negation of the true fact. And finding that specific part is extremely important, at least for now. Why? Because for that we need to go, I mean, although we are using n-grams to understand how we can find how we can spot fake news, but dealing with like even a very specific, like by narrowing down that problem is extremely difficult. So this is why I think if we really want to find the spot, okay, so for example here he is the second richest guy, and here it says no, he's not second richest guy, I think is very challenging.
Okay, and one more question that follows up from this discussion is that this involves a bit of a tweak, in the original news. But what about a fake news writer writing something completely else about Virat Kohli? I mean, it's not about his income, but it's about something else.
Okay, so basically I just like took this example just to like show how the samples look like in our data set. So not all the news are like that. So for example, here this news slightly tweaked the news article, but that was a very best example to show that like it is not necessary to change all the context when you write fake news. Even if you tweak a small number of words, can really change the meaning of the whole news. But that is only a one specific example. In our dataset, we have a plenty of different examples. So in some news articles where the fake news talks about different things. For example, if the fake news, the real news talks about sports, and specifically, let's say football, but the fake news will talk about baseball, or they will just trying to change some context. So in this example, this is a very specific example. So I just choose that because India, Pakistan, they love talking about cricket. So this is why I chose that example, in which I showed like only by changing some words can really change the entire meaning of the news article. Did I answer your question?
Yep, you did. Thanks a lot.
Yeah. Thank you. More questions?
I think that's all. Yeah, thank you, Maz.
Okay, so thank you very much. Thank you so much.
Yep. Okay. So next presentation is event detection from news in Indian languages, and presented by Bhargav Dave.
I'm audible?
Yeah, Bhargav, you're audible. Yes.
So I'm presenting a track, event detection from a news in Indian languages. So based on title, you can predict that this is a track in which you have to detect event or extract a event. So this track is part of a project, a platform for cross-lingual and multilingual event monitoring in Indian languages, sponsored by HRD Minister and now Education Minister of India. So I'm a Bhargav organizing committee member, and with me Surupendu and Prasenjit Majmudar and other team members will organize this track. So this is the outline. First is I will talk about the overview of track, then introduction, track timeline, track details, then corpus of a track, statistic of participants, summary of methods, top team results, and closing remarks. So now I'm starting with overview. So first of all, what is the goal of this track? So as I mentioned, detect the event from news article written in languages like Hindi, Bengali, Marathi, Tamil, and English. So next is, what is event? So it can be occurrence of happening in certain place during a particular interval of time with or without the participant of human nature. So here fire is one event which occur yearly and at particular time December, and it is in this event human nature involved. So this event may be a part of a chain of occurrence or outcome of effect of proceeding occurrence or a case of a succeeding occurrence. Like this event can be a naturally or it can be because of human action. It can be involve a location, time, or which agent like human or anything other involved or not. So this in this particular track, we go down to the only two events, man-made disaster and natural disaster. So in natural disaster, first example is current pandemic corona. So next is this is an example of flood which happened in 2013. One example is 26 is a terror attack which happened in Mumbai, and other left side you can see a picture of event Godhra Kand, that is riots, which is a man-made event. Next is train collision, car collision, then earthquake, natural event, natural disaster, tsunami, a natural disaster. So timeline of a track. Yeah. On 10 July, we open the registration and release train data. On 10th August, we release test data. 25th August, we release 25th August is a run submission deadline. And on 10th September, result was declared. And on 13th September, working not submitted by teams. So now I come to the first task of event is event identification, in which required to identify pieces of text from news article that contain an event. First is man-made, as I mentioned earlier. Second is natural event. In task 2 is event frame extraction, in which participant required to create an event frame from the news article. So this event frame consists of following fields: type, detected. The event frame consists of the following fields. First is type, maybe subtype of event, like in man-made, their subtype is accident. I will show one example in next slide. Casualty. So casualty, number of people injured or killed and damage to the properties, like in flood there is 100 crores loss happen, like that, required to take in casualty. Time when the event took place. Fourth is place where the event took place, like in previous example you see the flood which happened in Kedarnath. Reason why and how the event took place. Now I will explain a corpus which is developed by developed in a various institute from a different part of India, like for Marathi data set developed in IIT Bombay. So now this is a corpus file. In corpus file, we share the XML file. Each XML file represents one news article. Here, left side example or figure shows the man-made event. Type is accident. Type is accident. Sorry, type is accident. Accident occurred around 6:30 p.m. at the church junction on the state highway. So in this case, here man-made is an event and accident is a type. Yeah, and here event frame is time at 6:30 p.m. This particular event happened, and place is church junction. And on left hand side, natural event, earthquake. So here is subtype or type is earthquake, around a 5.5 Richter scale, and place is Japan. And time is Wednesday. Okay, so now I come to the corpus statistic. Yeah. Each news article present in different XML files, which I mentioned previously. So this is a statistic of data set. For English dataset, total 1034 article present, and in trained dataset 828 files, and in test dataset 206 files. So totally we share the 5630 files with a participant. Now statistic of participant. So total 22 team register for a track. Out of that, we receive 5 submission and 23 run. And total 4 teams submitted a paper in workshop. So this is a statistic of language-wise statistic of run. In English track, we receive for task 1 English track we receive five run, and for task 2 we receive 3 run. In Hindi, we receive 3 run for task 1 and 1 run for task 2. So maximum we receive 5 run for task 1 English. So total 16 run for task 1 and 7 run for task 2. So now a summary of methods in which I explain top top team. What method top team use? So first is 3D, which is with 3D. Subhanshu Mishra use Ngram and regex as a pre-processing, and they use CRF model. So here body date. Next is body shape, which submitted by Anand Subramaniam and his team. They use word level distributed distilled word, hashtag, and character level embedding, and they combine that thing and push to the bi-listing. They didn't submitted a paper in workshop, so but they are presenting paper in last session of FIRE. Now COM-MA, a team of Ritesh Kumar, they submitted his result in his result in 3 track, and his overall paper submitted in ANIL. So they use 3 method: XLM robot, distill word, and bot. So now I come to the result part. Top team result. First, I start with English. So here you can see that 3D receive F1 score 0.74 with traditional method, and other deep learning method not perform that much well than traditional method. So this is now Hindi language result. In this also 3D team first rank, overall 3D team first rank. So for Hindi, F1 score is 0.62, and here COM-MA F1 score is 0.51. So difference is around 0.10, which is huge. And for task 2, only 1 submission, 1 run from 3D team. So we can't compare that with others. In Bengali, same same like Hindi language. In Marathi, only two teams submitted, 3D and MUCS. So MUCS didn't perform well for task 1, and MUCS also didn't submitted for in task 2. Now for Tamil language, same 3D and MUCS submitted a run, and MUCS didn't perform well. So now last closing remark. We successfully released a multilingual dataset for news event detection. From observation of result, traditional methods perform well rather than deep learning methods. We are planning to extend tasks by linking one event to another if they are related to each other. We also plan to introduce summarizing of event. So for this, annotators required who can create a gold standard dataset of event-based summarization, which may require significant amount of time. So, any question?
Hi, can I ask you a question?
Yes.
So I saw from your results that the 3 idiots team did quite well because they used regular expressions, right? I mean,
Yes.
character engrams with regular expressions. And in comparison to that, the BERT-based methods, they weren't doing that well. So my first question is, were the BERT models trained specifically for Indian languages? And if so, then what could be the reason that the BERT models are not doing that well compared to simple approaches like regular expression? So what do you think is unique in the data set that might have caused some simple approaches to work well?
Maybe this is a very small data set, I think. And this is a very small data set, and that event like man-made and natural disaster event is distributed not very much well. So maybe that one reason that particularly for this problem, we able to that 3D able to perform well because of this rejects and engrams. Maybe Surbendu can answer this question because I have less knowledge about BERT. Surbendu?
Well, I think they train the models separately on each and every language. But from what I understand is that the pattern in which the different news articles or have been written, that may not have been somewhere. It may not have been learned by BERT. That is what I think, and including the size of the data set may also play a huge role here.
Yes.
Yeah, because these even though this is one language we are looking at, the various events that are there, that's highly imbalanced, and that is where I think BERT is not able to handle it properly, the imbalanced data. And yeah,
When you say that they trained BERT on Indian languages, did they train the language modeling task of BERT?
I don't think so. I think it was just fine-tuned on, I didn't see that. It was just trained on sequence classification task, as a sequence classification task, that's all.
Okay. No, but then I think the problem is, like, if you are using pre-trained BERT models, right? So they are trained in English, and the language model that they have is essentially of English, right? And then even if you fine-tune BERT on your task, then that's not going to perform that much well, right?
Yeah.
You need to train the language modeling task of BERT on Indian languages.
I think there are some multilingual BERT.
BERT as well, yes.
Yeah, multilingual BERT cased or uncased that is available. I think they use that and then they just fine tune on it straight away.
Yes, but even then, I think for a multi-language case, I think English dominates over the other languages.
Yes,
right? So,
yes, of course, yeah.
For low resource languages, like, I don't know, for even maybe Hindi is not that low resourced, but Marathi and I don't know some other languages, I think they're less resourced than English, right?
Yes.
So in a multilingual setup, I think it's very easy to dominate or have dominating effects from European languages and then look out on the Indian language side of things.
Yes, exactly.
Okay, thanks.
All right. Okay. So that brings us to the end of the track overview presentations. Yeah. Parth would like to say a few words before we move ahead.
I just would like to thank all the track organizers for your wonderful efforts. So we had the most number of tracks since FIRE started, 10 tracks this time. And also naturally the most number of participants. And some of you have been with us for years, and some of you I got to know only this year. I wish that I could have met you in person. Unfortunately, that couldn't happen this year, maybe next year. But thank you, all of you, for your efforts, and running everything online wouldn't have been easy, but it went well. So thank you, everyone, and thanks to Thomas as well. And hopefully, a lot of you will continue next year, maybe with the same tracks, with new tracks. And hopefully, we'll see you next year in a location where we have been wanted to go since years now. Those of you know it's a secret, it's still not official, but hopefully it will motivate you to visit us next year. So yeah, thank you, everyone.
And thanks to you, Parth. Thanks to you as well.
All right, over to you, Shuru.
Yep, thank you, Parth. Yep. Okay, so now we move ahead with the short paper presentations, and the next presentation is on the evaluation of data fusion for information retrieval, presented by David Lillies.
Hi, everybody. I hope you can see and hear me.
Yep. Hi, David.
And hopefully now you're looking at a PowerPoint presentation. Greetings from Ireland. I would prefer to be in Hyderabad, but here we are. Thanks for the opportunity to talk. So I'm going to talk about my paper on evaluating data fusion for information retrieval. So I think the first thing to start with is, what do I mean by data fusion when I use that phrase in this context? So here we have, I guess, a form of classic ad hoc retrieval, really. We start with a document collection, and we want to finish with a set of results that go to a user. And in this setup, we have individual systems all retrieving from the same corpus, and they each produce a set of results as a normal ad hoc system would do. And then following that, we have a fusion component. So this is where the data fusion comes in, that essentially merges these sets of results into one result that can be given back to the user. And hopefully that's better than what the individual systems can produce by themselves. So in terms of this particular paper, it's a short paper, and I can just give a quick summary now first, I guess, which is essentially what I was doing with this paper is I had a look at approximately 30 papers relating to data fusion, and I wanted to examine how is evaluation done when people propose these types of approaches. And the main conclusion that I came to is that evaluating this is actually not done particularly consistently. So no unified way of organizing experiments, choice of evaluation metrics, choice of data sets, etc., has really emerged. But what I really wanted to do then was to identify kind of common approaches that people have taken, and more importantly, shortcomings, and particularly common shortcomings, where the evaluation potentially could be designed a little better, be a little bit more robust, and so on. And then some suggestions on how evaluation should be done for data fusion tasks. Now, because I only have a short presentation, I've only got 10 minutes or so, rather than try to go through all 30 papers, I decided to pick one case study, a little dangerous. There's the title there. And to say, why did I pick this particular paper? Well, first of all, it was peer reviewed at CIR. So that's at a leading IR conference, or the leading IR conference. To date, it's been cited 99 times. So between these two facts, I guess it shows that there's some validation from the community that this is, this is not just some random paper. It has some examples of some of the common evaluation issues that I spotted throughout reading these 30 papers. And it's important to say none of these are unique. So none of the problems with this particular evaluation are unique to this. They happen in other places as well. And just before you think I'm being tremendously cruel picking on one poor set of researchers, the other reason that I chose this paper is because I wrote it. This is something I've reflected on since. So I think I'm allowed to be mean to myself in showing some issues. So just to show how that particular paper was set up, as is commonly done, some TREC runs from ad hoc tasks were chosen as the inputs. So the various participants' runs are available. We ran these experiments 5 different times with different inputs each time. And each time we ran an experiment, we chose 6 inputs to merge together as part of the data fusion task. And we even ran those 5 times with random orderings of topics to try to reduce some potential influence of bias. We used a common baseline COMB-MNZ. It's a pretty old one, but at that time in particular, it was commonly used as a baseline to see could a new data fusion system improve upon this. And we evaluated using MAP and BPref. And the results that were published in that CIR paper look a bit like this. So we have got the results from the baseline for 5 different experimental runs for MAP and BPref, along with some averages. We had our own results for MAP and BPref, and we had said, this had improved or disimproved upon the baseline by certain percentage amounts. And really, when you look at this, you can dig deeply into how it was set up, and you can dig deeply into what this table is telling us. And the first thing that's missing, and again, I emphasize, none of these are unique to this particular paper. I'm just picking one example. Is the use of fusion justified at all? You can conclude that we've improved on a baseline, great, but there's no comparison with the actual underlying systems. Maybe we would have been better off just choosing one of the inputs, because when we merge their results into one set of results, we could be making it worse. And that's not captured in this particular experimental setup. A second observation is, and I'll come back to this in a minute, what is the upper limit here for MAP and BPref? So we've said that we can increase it by a particular amount, but as we'll see in a moment, it's not clear what the possible improvement could have been. There is no statistical significance tests. So, to what degree are these differences significant, or could it be based on a small number of outliers? There's only one choice of baseline, and there are other studies that also claim to have improved their performance compared to COMB-MNZ or other baselines. So the cross comparison between these is quite tricky. The whole idea of percentage increases or decreases is quite problematic in and of itself, and there's huge limitations to what those can actually tell you. Obviously, if you start off with an evaluation score of 0.16, you could improve that by 500 or 600%, whereby if you start off with 0.43, you can only get slightly over 200% of an increase. So in one respect, these are nice to look at, but in another respect, they're not particularly informative because of what your starting point is, and as I mentioned before, what your upper limit is. And the other issue then is the reproducibility. So this predated, to be fair, the habit we have now of making things available on GitHub and places like that. But also because there was a randomization element here, the input topics were shuffled before each run. It does mean that although other researchers could reproduce this methodology, they probably wouldn't be able to reproduce these precise results. And that's not a great feature when we're talking about science, essentially. So let me just come back to this idea of the upper limit, and this diagram again to show that from start to finish, again, to get from a document collection all the way to a user, this is the same as a classic ad hoc task. But when we only focus on the fusion, the inputs that we have available are the outputs of other IR ad hoc systems. And this means that these do not necessarily make all of the relevant documents available to us, because there may be relevant documents in here that have not been actually retrieved successfully in the first place. So I wanted to explore that with a view to looking at what these upper limits might be. So I ran a quick experiment based on ad hoc results from the TREC 2014 web track. And I chose the top 4 systems as determined by NDCG and the bottom 4 systems under the same measure. And I fused them perfectly, as in taking the results that were produced, only take the ones that I know to be relevant and rank those in order. And we discovered that actually, unlike most evaluation metrics where 1.0 is perfect, 0.0 is, you've done no good at all. In fact, if you were to actually fuse, for example, the results from the bottom 4 systems, the maximum recall you could possibly achieve is only 0.62. So we're no longer operating in the scale between 0 and 1. And of course, these numbers aren't directly comparable due to difficulty in queries and data sets and so on. But we do like normalization. That's what the N in NDCG is for, after all. So I'm arguing, I suppose, that this is a slightly different challenge to classic ad hoc retrieval when we're only evaluating the fusion part. So based on all this analysis, essentially what I'm trying to do is come up with some recommendations for anyone who is writing papers like this in the future. And I see this talk really as I suppose, an advert for the paper. If this is something that is of interest to you, it's only 4 pages, so give it a read. So the first recommendation, I think we need to justify the use of fusion. So the inputs themselves should be the baselines. We should be able to beat the best system overall, and possibly on a per query basis as well. There's some rationale for that as well. Rather than using the classic ad hoc metrics by themselves, I suggest that maybe we need to normalize for the relevant documents that are available to the fusion system if we're comparing with other fusion approaches. The idea of percentage increases, which again is not just unique to that one paper, are not particularly useful, and I don't think we should be using those. Statistical significance tests should be a feature of this type of work as well. And finally, the idea of reproducibility. We should be continuing the habit that we have now of making code available, especially for more complex kind of techniques that are more difficult for people to implement themselves. For the classic simple ones, implementations are quite straightforward, so there's less problems with that. I would suggest that perhaps we should integrate with the TREC tools project, which João Palazzi introduced at CIR last year. Feels longer than last year, but there we go. That's on GitHub as well. So perhaps we should be targeting that framework and library for any implementations we come up with. And rather than randomization for any systems that need kind of a training test split, we should be using something like tenfold cross-validation instead. So that's me slightly over 10 minutes, so I won't keep you any longer. Again, just to try to give an overview of what the paper is about, and if it's of interest to you, 4 pages, have a look. Thanks, everyone.
Any questions from the audience?
Yes, I have a question. Hello, David.
Hiya. How you doing?
Yeah. So I have contributed to your basically 99 citations because I cited your paper in one of my papers.
Thank you very much. If you want to cite it once more to say it's terrible, that would be very welcome.
No, I have been trying to do that, but you see that not many people are, I mean, really working on this area anymore. If you see that, so you won't find, I mean, too many papers on data fusion at in venues like, I mean, CIR or CIKM. I don't know why. And this actually captured my interest when I was doing my PhD. So I mean, wrote a paper which actually improved I mean, fusion performance using, I mean, genetic algorithms. So I think I compared with your paper. So, but that is, I mean, not a fair comparison because that was a supervised, I mean, a method. But I mean, my question to you is, in your paper, I mean, did you compare with the best performing input method? I think you mentioned it in the last slide. I mean, so I mean, suppose you are fusing 2 or 3 runs, and the fusion does better than a baseline. For example, it can be COM-SUM, COM-MNZ, anything. But if the fusion method is not improving over the best input method, then it doesn't make sense, right? Because I mean, because you already have the best system with you, then you don't have the motivation to fuse them, right?
Yeah, precisely. And I think that's the argument, because there's several papers that only compare with other fusion methods.
Yeah.
But there are, of course, situations where combining results from various systems, you can make it worse. So your input systems could be one very, very effective system and some not so good ones. And the reason why I've kind of raised this is because I think as part of the evaluation, we have to justify why are we fusing at all?
Yeah.
Because two ways that I can see quite easily to figure out as baselines is, one, can you beat the best system? That's straightforward. Or without having to merge individual sets of results, could you, if you had a number of systems that were quite similar in their overall performance, would we be better researching you know, result selection? So we say for the first topic we get, maybe we should figure out that system A is better, and for the next topic system B is better, and then maybe we should be directing our attention from a research perspective on how do we pick the best set of results, as opposed to how do we combine them together.
Yeah, of course. And also, I mean, when you are basically, I mean, randomly picking, I mean, basically runs to fuse, then that will also, I mean, preclude, I mean, generalizability, right? Because I mean, a random method cannot be generalized. I mean, cannot be basically reproduced by another paper, because the set of runs which you are comparing in your paper will be different from what they will be doing, right? So
yeah. So I think in that particular paper that I chose as the case study, we did say which participants' runs we had used, but then because the proposed system required training and test splits, there was some shuffling going on, and we didn't include that. So you could mostly reproduce what had been done, but you weren't going to be able to verify that those exact map scores were what you were getting.
And also, I think there is something about the number of runs you are choosing and the type of candidates which you are choosing, because I mean, this I found in, I mean, while I mean doing some experiments. So when you are choosing I mean runs which are already, I mean, superior, then fusing doesn't produce any improvement over the better one. But if you are considering a pool of runs which has some good methods along with some, I mean, average performing methods, and then I mean, if you combine them and possibly with more weightage to the better method, but I'm talking about a supervised setting, then then the improvement can be significant. So that was my observation.
Yeah, I think that tallies with mine as well. And there's been some studies, I haven't read them recently, to be honest with you, about, you know, input selections, and does picking the best systems necessarily work the best, because there may not be enough cross diversity between them,
right?
And diversity might improve things more than not. I didn't really go near that with this paper. I was looking at kind of the more, I suppose, non-controversial things that I could say that seemed like common sense that we might apply going forward. And I agree with you, there's not a lot of people working on this, and you'll have seen from the date that the paper I wrote was not new either. But it's just been something that's been nagging me a little bit since I got older and more experienced as a researcher, because I wrote that paper as a master's student myself. And the more I look back on it, because I teach a class on this, so I have to look at this every year. And I thought I should put some thoughts down and send it in as a short paper, as a thought piece. So
I mean, thank you very much for doing that. At least I got someone presenting something on, I mean, this topic, which is, I mean, not, I mean, seem to be out of, I mean, interest for the CLEF community or information retrieval community. So thank you for the paper.
And thank you for the comments. Nice discussion.
Yeah, thanks.
Do I have time for one question, Shubhendu?
Yeah, of course, you can.
Hi, David. So I wanted to ask you one question. So you mentioned that, you know, this baseline against which you want to compare is the best run among your fusion approaches. So I was wondering that, you know, maybe what if we compare, let's say, you know, we imagine that there is the best interleaving that's possible, right? So we walk down the rank list, you know, at each position, you know, let's say we have got 8 choices, right? And we take the one that's giving us the relevant document in that position, right? So, you know, if there are 3 choices or 3 lists to pick from, you know, if we're at the 5th rank, then we'll pick up, you know, that particular list, you know, which has got relevant document at 5th position. And if we do that for every position, right? So then it means that, you know, we can, you know, if we think about interleaving strategy, that will give us the best possible, you know, way to combine, you know, if we have an oracle like that. So do you think that it makes sense to compare against that oracle in these settings?
So I guess the idea of I think it's reasonable to have several baselines and several oracles, some of which are more feasible than others. Right. Interleaving at the rank level directly is, you know, most of this is kind of based on an overall picture of, you know, what scores have been apportioned by different systems to it, or sometimes done by ranking as well. But, you know, the better systems, you'd take more from the earlier ranked positions rather than look at each rank individually. But the idea of the normalizing the metrics for fusion is I think kind of what you're saying. It's you're going down to the input result sets. You know in advance for evaluation purposes which the relevant and non-relevant documents are going to be. So you're choosing only the relevant ones, right. And that's your perfect fusion. So that's kind of related to the upper limits that I mentioned, that for, you know, when I said I think that the top 4 ad hoc runs, the maximum map score you could actually get was 0.86 or something like that, as opposed to 1. And that's the limit of your ambition. You can't get any higher than that, because earlier on in the process, you've already lost some relevant documents that the individual systems haven't picked up.
Right. Yeah.
And I mean, there's all sorts of discussions you can have about, you know, the nature of pooling and things like that, and incomplete relevance judgments and so on. And another thing that you can acknowledge complicates the situation, but I kind of try not to get into that and focus on let's assume that the way we evaluate normal ad hoc retrieval is fine, and then if we're working within that framework, what makes sense for this task, because I do think it's slightly, it has its own unique features that haven't really been addressed in a lot of the literature. There have been, I should say, and I haven't said this, there have been the odd really, really good study that is very comprehensive in how they've evaluated their work, but they haven't always been picked up by future researchers as well. So there's a mention of a couple of those in there too.
Okay, thank you.
So I mean, one just passing comment. I mean, since you brought it up, so I mean, do you think data fusion can help in improving the quality of, basically the pooling of, ad hoc methods? Because you are creating a pool from the participating runs, right? And if we are able to fuse the participating methods in an efficient way, that would basically bring up the relevant documents, and that basically can automatically enrich the pool.
Yeah,
it's certainly we certainly can't discount it, because those different individual systems can have different pre-processing steps, different ways of dealing with things like stemming, lemmatization, and so on. Different stop word lists, for example, if some are using that or not, as the case may be. So you can certainly increase the recall over using one individual approach that's quite constrained. But then you can argue that do you replace the entire system, or do you just replace parts of the process? Because those systems are themselves a pipeline involving parsing the data, parsing the documents, and tokenizing them in some way, and using some kind of a mathematical model to come up with a ranking score at the end of it. But it's certainly, in my view, I think it's a valid approach, and if we are using it, we should be evaluating it properly.
Yeah, of course. Thank you very much.
Thanks.
All right, thank you, David. Yep. So we move ahead with our presentations. So the next presentation is on performance gain in low resource machine translation with transfer learning and analysis concerning language families, presented by Sainik Kumar Mahata.
Am I audible, sir?
Yep, you're audible.
Okay, so is the PPT visible?
Yes, your PPT is visible.
Okay. Good evening, everyone. This is Sainik Kumar Mahata from Jadavpur University, and today we will be presenting our work on titled Performance Gain in Low Resource Machine Translation with Transfer Learning and Analysis Concerning Language Families. For the introductory comments, we all know that a machine translation is nothing but translation of one natural language into another natural language using the help of computer software. But for a machine translation system to work, it requires a parallel corpus to learn the mapping between the two natural languages, the participating natural languages. And after the advent of neural machine translation, the size and the quality of such parallel corpus is a very important deciding factor to generate high quality translations, which means that better the size and quality of the parallel corpus, the more better the quality of the translations will be. But if either of the participating languages, which means either the source or the target, is low resourced, the large and quality parallel corpus that we talked about earlier becomes unattainable, and hence the performance of the machine translation also degrades. So to counter this, there has been recent trend of using multiple languages as a source or target to augment the scarce data of the low resource languages. So what was the motivation of this work? We know that, or from it has been studied as well, that a native English speaker, which means if an Indian speaker who knows English as well as knows Hindi, he or she may be able to learn Marathi easily compared to someone with who has zero knowledge of Indian languages. It has also been studied that the ease of learning a third language for bilingual speakers directly depends on how distant the languages are. So which means if in this example, if a person who knows Hindi may learn Marathi quite easily as compared to Bengali, for example. So we wish to investigate if there is performance gain in an empty system when it is trained using a load source parallel corpus. Example, language L1 to L2. So L1, L2 parallel corpus, where L2 is a load source language, while employing transfer learning from a high resource parallel corpus from language L1 to L3. So we have an example. So if I have L1 and L2, suppose we have an English Marathi translation system, and we have a high resource translation system that is L1 to L3, that is English and Hindi. So whether if I train a system using English and Marathi, whether another system that has been trained using English and Hindi can help the first system to generate better translation results. Also, we want to investigate that the position of L2 and L3 in this case, which means, for example, Hindi and Marathi, if they belong to the same language family, whether that also helps in the gain in performance of an MT system. So for the data, we did our experiments on the Indo-European and Indo-Aryan languages. So for the Indo-European languages, we considered four language families, that is Baltic, Slavic, Finno-Ugric, and Romanic. And for each language family, we can see that for Baltic, we have a Latvian dataset, so English Latvian dataset, that is considered as a high resource dataset, and it contains 500,000 data. And again, we considered another parallel corpus, that is English Lithuanian, and we consider this as a low resource data set, and it contained 100,000 data. So similarly for Slavic, we had Czech English Czech language as the high resource parallel corpus, and English Slovak language as the parallel corpus as the low resource parallel corpus. Similarly for Finno-Ugric, we had Hungarian as the high resource and Estonian as the low resource. And for Romanic, we had Spanish as the high resource and Romanian as the low resource. For the Indo-Aryan experiments, we considered three language families. One is Magadhi, and Bengali belongs to this family. The second is Maharashtri, that is Marathi belongs to this family. And the third one is Hindi, that is Hindustani. So Hindi belongs to this family. And in this case, in the case of Indo-Aryan, we had English Hindi as the high resource parallel corpus. So that had 500,000 data. And for the low resource corpus, we had English Bengali and English Marathi that had 50,000 data and 48,999 number of parallel sentences. And these are the data source. The Indo-European languages parallel corpus were collected from Europal. For the Indo-Aryan, the Bengali and the Marathi corpus were collected from TDIL, and the English Hindi corpus was collected from IIT Bombay corpus. So now coming to the framework that we used the state-of-the-art transformer-based encoder and decoder architecture. And now, why did we use this? Because basically, previous to this, we always used RNNs, sequence-to-sequence learning architectures. Now, normally, since RNNs are sequential, they can't take advantage of the parallel computing offered by state-of-the-art computing devices. On the contrary, the transformer models rely heavily on self-attention, thus eliminating the concept of recurrence found in RNN-based architectures. So, and obviously, it is currently the state-of-the-art in terms of machine translation research. So we used the framework designed by Vaswani et al. From the paper "Attention is All You Need." Now, with the concept of transfer learning, we wanted to keep the source language unaltered across the whole process. So the source language in this case is English, and we augment the encoder of L1, L2. So in this case, if I take the previous example, so if L1 is English and L2 is Marathi, so we augment the encoder of English Marathi transformer model with the weights of the encoder of the L1, L3. So L1, L3 in this case is English and Hindi. So we augment the encoder of English Marathi model with the weights from the encoder of the English Hindi model, and compare the performance gain with the baseline model, that is L1 and L2, which means English and Marathi. So we have the example here. We further investigate whether the degree of frequent word sharing between L2 and L3, so that is Hindi and Marathi in this case, whether the degree of frequent word sharing correlates to the MT performance gain. So for the low resource MT system, so if I have the English LR, that is let us go by our example. So if it is English and Marathi, we call that system as the LRMT system, and that will act as our baseline system. And again, we have a HRMT system that will be trained as per our example using English and Hindi. So we have two systems, both based on transformers. One is the baseline system is English Marathi, and the HRMT system is English Hindi in our example. So this is the model that we used, and these are the parameters. Now for the hybrid model, that will take into account the weights of the encoder of the HRMT model. We used a custom layer or a merge layer that will aid us in doing so. So the hybrid model was trained using the English LR language pair, so which means English Marathi in this case. So this encoder, or this the model depicted using a dotted line, is the LRMT system, which means this encoder and decoder is for the English Marathi translation model. And this HRMT encoder shown in orange is for the English Hindi. So we take the encoder of the English Hindi translation model, and we take the weights, we merge the weights with the weights of the encoder of the English Marathi encoder, and then jointly we provide the output to the decoder of the English Marathi translation model. Now this is the merged layer. We have the equation. So first and foremost, what do we do is the merge layer. So initially, the output of the HRMT encoder is provided to a feed-forward network and is passed through a sigmoid function. Now what this does is generally acts as a attention layer, which means the output of the sigmoid function will be 0 and 1, so in between 0 and 1. So whenever we multiply, or whenever we bitwise do product of the output of this with the range between 0 and 1, all the important parts of the learning will tend towards 1, and the less important parts will tend towards 0. So the important parts are then bitwise added to the output of the encoder of the LRMT model, and then it is given to the decoder for further processing. Now for the results, we had two metrics. One is vocabulary sharing, and the second one is MT performance. Now for the vocabulary sharing, we wanted to investigate the degree of word sharing between the different experimental languages. And in our case, the vocabulary intersection was calculated as the fraction of common tokens covering the full unique token sets of each language pair within the language family as well as outside the language family as well. And for the empty systems, we had 6 LR empty systems, as because we have 6 LR languages, and we have 5 HR empty systems, as because we have 5 HR languages. And so for every one LR empty system, we had 5 HR empty systems. So in total, we had 30 LR empty hybrid systems. So again, we have given an example that if there is a LR system that consists of parallel purpose English and Marathi, this can be augmented using English LT HRMT encoder. It can be augmented using the English Czech weights. It can be augmented using the English Hungarian weights. It can be augmented using the English Spanish weights, and so on. So in total, there were 30 hybrid systems. Now these are the results. So we can see that again we have the language families in the first column. The second column has the name of the LRMT or the corpus that we use for the LRMT systems. So for Baltic, we had the English, we used the English-Lithuanian parallel corpus that was considered as low resource to train our LRMT system. For Slavic, we used English-Slovak parallel corpus. For Finno-Ugric, we used English-Estonian, and so on. And for the hybrid system, so this English-Lithuanian system was augmented using the weights of the encoder that was trained using the English-Latvian language pair. So we name the system as so English Latvian will be fed to English LT. So we name it as Latvian and Lithuanian. So again, we have the blue scores for the LRMT systems that was considered as the baseline system. And for the hybrid system, again, we have calculated the blue scores. And this column, the last column, signifies the difference in blue scores between the baseline system and the designed hybrid system. Again, with the help of this scatter graph, scatter plot, we can also see that we can also map the performance with respect to the vocabulary intersection. So in this case, if we consider the topmost point, this is English, English Czech and English Slovak. So which means that if we come to the Slavic language family, the LRMT system was trained using the English Slovak, and the hybrid system was augmented using the English Czech encoder weights. So we can see that the vocabulary intersection between Czech and Slovak is very high, as well as we can see that the difference in blue score is also considerable in this case. So again, if we come to the next one, we can see that this is Hindi and Marathi. So again, if I come to the Maharashtrian language family, so the low resource MT system was trained using English Marathi parallel corpus, and the hybrid system was so the English Marathi model was augmented using the English Hindi encoded weights. So again, we can see that there is a high vocabulary intersection between Hindi and Marathi, as well as this corresponds to the considerable amount of blue increase in this case. So similarly, we have it all. Again, in the last section that is denoted in red, we can see that there are various language pairs here. So that is Hindi and Bengali, for example. So obviously we know that there is very less vocabulary intersection between Hindi and Bengali language. So again, since the vocabulary intersection was very low, the difference in blue score was also very low. Similarly, we have it for the other languages as well. So from the scatter plot and the table that we had, we can come to the following conclusions, that more the word sharing between two languages, more the two languages will help each other in MT performance gain when object transfer learning is used. Again, we can observe that the Indo-European languages within the same language family have higher vocabulary sharing as well as high gain in performance with the hybrid model. And lastly, we can see that the difference in blue scores is better in Marathi. Obviously, we discussed it earlier because there is a high vocabulary intersection between Hindi and Marathi, and the scores for Hindi and Bengali were less because there is low vocabulary intersection between English and between Hindi and Bengali languages. So to conclude, so in this paper, we investigated the performance gain of a low resource MT system when augmented with a high resource MT system. We correlated this gain with the vocabulary sharing between languages when the language belongs to the same language family. We can see that the high resource MT systems does help a low resource MT system to translate better when both the languages belong to the same language family. And we find that the degree of vocabulary sharing between languages correlates to the performance gain during translation. And in the future, we would like to explore other languages as well that has diverse linguistic characteristics. So that will be all. So thank you.
Any questions from the audience? All right. Okay. Thank you, Saini. Thank you.
Okay, thank you.
Yep. Okay. So next presentation is on unsupervised legal concept extraction from Indian case documents using statutes by Riya Podde.
Am I audible?
Yep, you're audible.
I think screen share has to be stopped. I'm not able to. I'm getting. You cannot see. Yeah.
Yeah, just a minute. Saini, can you just stop the screen sharing? Yeah. Okay. Yeah, your screen is visible now. You can start.
Okay, great. Yep. Hi all. I am Riya Sanjay Poddar from VIT Vellore, and my co-author is Paheli Bhattacharya from IIT Kharagpur. And I'll be presenting on unsupervised legal concept extraction from Indian case documents using statutes. So the challenge is that in India, we follow the common law system where emphasis is given to precedents. And that's why legal practitioners have to go through these precedents when solving ongoing cases. These precedents are basically prior court case documents decided on by important courts like High Courts or Supreme Court of India. And they are unstructured, extensive documents without keywords. So, legal concepts or keywords can provide information to the practitioners at a glance, thereby saving precious time and effort. So, our motivation behind using statutes for legal concept extraction is that after discussions with law experts from Rajiv Gandhi School of Intellectual Property Law, IIT Kharagpur, we understood that statutes are rich sources of legal domain-specific information. They are relevant laws cited in the case documents, and they can be used to retrieve legal concepts which are present abstractly in the documents. This is unlike in the case of catchphrase extraction as seen in other previous works, which retrieves words explicitly mentioned in the documents. So, coming to the objective, now each statute has a title and description. So, here is an example of a statute, IPC section 302, whose title is Punishment for Murder and description is as such. Now, there are statutes that discuss similar or related matters. So, given are two more examples of statutes. If we observe the title of each of these three statutes, we can see that they are talking about the same common topic, that is punishment for a particular crime. So our aim is to basically cluster such statutes together which discuss about the same topic. This topic shall then represent related statutes collectively. Subsequently, it can be used as a legal concept in a document that cites any statute from that corresponding collective. Coming to the methodology, so this this is a pictorial representation of one of our proposed methods. And here the nodes S1 to S10, they are representing statutes. So these are vectors. The edges are established between statutes having high degree of textual relatedness. Then different groups of communities or clusters are formed, and community-wise topic modeling is done, which gives us topic sets for each community. And a document cites statutes and based on the statute community, corresponding topic set is retrieved. This will form the legal concept of the document. So in this example, we have document D1, which cites statute 3 and 9, and therefore topic set 1, to which S3 belongs, and topic set 4, to which S9 belongs. These are retrieved as the legal concept. And here we can see that the legal concept which we are extracting was not explicitly mentioned in the document, but it is abstractly present through the statute cited in the document, and that's the basic idea behind our method. So for the implementation, we have proposed two methods, LuvaCom plus LDA and K-means plus LDA. So the first step is common, that is we are representing the statutes as TF-IDF vectors. We are using statute description for that purpose. And then after that, we come to method 1 and 2, LuvaCom plus LDA and K-means plus LDA. So I'll be talking about them parallelly. LuvaCom plus LDA, in that we are using these TF-IDF vectors as the nodes. An edge is established between statute pairs if they have a cosine similarity value greater than a particular threshold. Then Luva community detection algorithm will be applied to that graph. So we get communities. Parallelly, if we look at method 2, that is K-means plus LDA, here we are using the statute vectors and clustering them based on the distance between the vector and the seed using K-means algorithm. So now the next two steps are common to both the methods. So after we obtain the community or cluster, we are using LDA for topic modeling on the community, which will give topic set. And finally, given a case document and statute cited in it, we retrieve community of statute and then the topic set, and that forms the legal concepts for that case document. All our data has been collected from Westlaw India website. And important thing to note is that the number of seeds which we selected for K-means plus LDA method is equal to the number of communities detected in LuvaCom plus LDA method for fair comparison. Legal concepts acquired for each case document were unigrams. In case of baseline methods, we have taken two baselines, PS legal and a dictionary-based approach. So in PS legal, we are scoring the words. PS legal is a previous work in which the words are scored, in the words from the case document are scored. And from that, we have taken top 15 catchphrases. In case of dictionary-based, we are using a legal dictionary to extract legal words from a case document as catchwords, which are then ranked according to the TF-IDF value. And then we are again extracting the top 15 from that. So that becomes the catchphrase for each document. And coming to the results, the quantitative analysis as seen in the table, our methods LuvaCom plus LDA and K-means plus LDA have significantly outperformed both baselines. Best performance is seen by K-means plus LDA, and LuvaCom has comparable performance. We are observing such results because our methods can extract the implicit legal concept, unlike the baselines, which are only capturing the explicitly mentioned words in the document. And when we look at the manually curated keywords by legal experts, it is not necessary that those keywords will always be from the document itself. So that's why our methods are giving better performance. And qualitative analysis. So here is an example, like this is LuvaCom method, and this is example of one community detected by one of the communities detected by this method, and the statute, some of the statutes in that community. And we can see that these are the statute titles. We can see that all are talking about the same topic, that is punishment for a particular crime. The other example is with K-means, we are getting this cluster and some of the statutes in it. And all these statutes talk about the same topic, which is constructing buildings without a sanctioned plan. So this shows that like our result was able to cluster similar statutes to a great extent. And this has much utility in other downstream applications like document similarity. So I would like to conclude by saying that our purpose was to extract legal concept using statutes, and for that we clustered statutes that discuss similar legal issues, and we proposed two methods, LuvaCom plus LDA and K-means plus LDA for that purpose. The results show the utility of considering similar or related statutes. As future work, we would like to use embeddings instead of TF-IDF vectors to represent a statute, and also like to experiment more on the topic modeling aspect of our methodology. So thank you all, and I'm open to questions now.
Hi, Ria. So I have one question.
Yeah.
So basically, what I understand from your presentation is that you were kind of clustering the document collection that you have, right? So you're while trying to find the statutes of a legal case, you are assuming that if you cluster the collection, it will be easier to find those statutes given a case, right? Am I correct?
Actually, what we are doing is like there's a data set of case documents, and we know the statute cited in that case document. We have that data. We are actually clustering the statutes, and then so I'll just so we have this suppose this is a case document, and each case document is citing some statutes, and the statutes are being clustered, and we are getting some common topic for that statute, and based on the citation we are retrieving that topic, and then the union of those topics from the legal concept. We are not clustering case documents in this.
Okay. No, okay, I understand that. So basically, you have a graph of the statutes that are linked between one another, and then you are clustering this graph, right? And then you are assuming that every cluster, in that graph that corresponds to one topic.
Correct.
Is that okay? And then so why
It's not
are you
one
applying
topic.
so?
It can be a topic set, like
So my question then would be, so this one cluster, or each cluster that you obtain, that corresponds to a particular topic that you are estimating it to be belonging to one particular topic. So how is LDA brought into account in this case? So on one hand, you are using the document connectivity or the links between the statutes, as a hint to kind of infer the clusters. So that's on one side of things. Is it the case that you're also considering the document content as well, in the LDA side of things?
Yeah, like so through the TF-IDF vectors we are able to link the statutes, but we need to use LDA so that we can get the important topics from the statute description. So the statute descriptions will be the input. So like in this cluster, suppose there are these 3 statutes, and all the statute descriptions will be the input, and from that on that we're applying LDA. We get the important topics out of it, like what the statutes are discussing.
Okay, so these links are not explicit links. These are links that you infer from the TF-IDF vectors from the content of the documents, right?
Yeah. So if the cosine similarity value between the statute pair is greater than a particular threshold, then we are linking the statutes.
Okay, so this very graph that we have built, it depends on this threshold, which acts as a parameter and kind of controls the link structure in this graph, right?
Yes, right.
Okay. So how exactly is LDA applied? So when is the LDA process applied?
After this graph is constructed, we applied LuvaCom and Luva community detection. We got the communities, and in each community, whatever statutes are there, we collect the statute descriptions, and on that LDA is being applied, which will give me a kind of list of all the important words coming out from that statute description.
Okay.
Yeah.
Thank you.
All right. Thank you, Ria.
Thank you.
So we head forward towards the last presentation for the day. The next presentation is Evaluating Professional Search, a German construction law use case, presented by Wiley.
Thanks. Hi, everyone. Can you see me okay?
Yep.
Yeah, great, thanks. So hi, everyone. This is Wei from Dublin City University, and I'm going to talk about the evaluating the professional search, a German construction law use case. So for some time, the professional search is referring to some domain-specific search. Usually the professional searchers are going to conduct a search on their specific domains. And it covers a lot of domains like the medical search, legal search, patent search, and some other stuff. So today our paper is talking about the legal search. And the motivation of our research is that we collaborate with the German legal companies, and their company has the the legal search engines based on the Solr, and every time when their lawyers want to search something, they need to create their query themselves and input some legislation links based on their legal professional knowledge. And they're going to conduct a search, but usually they need to refine their query several times until they find the true relevant documents they want to see. So this is our motivation. We would like to help them to improve their search effectiveness. And the challenge for our work is that the search on legal domain is already a challenge. And this is on the German language, so it's even harder. So the evaluation is a big challenge for our work because, doing the relevance assessment to conduct the evaluation is quite time consuming and money consuming. So it's really expensive. So our paper is going to address the evaluation part to create the task collections to address the evaluation for this legal search, task then. So what we have, the first document collections, and since we collaborate with a company, so they provide the real-world legal cases document collections based on the topic of German construction law collection. And it include over 1 million court German language decision documents in the XML format. And time spans for all these court decision documents are from 1950s to 2017. So each document pertains to the court decision for one case, but it happens that multi-documents are talking about the same case because one case can be processed by the local court, and middle court, or high court. And along with the document collections, they also provide the taxonomy collections, which are presented in the hierarchical structures. And it includes 4,636 legal concepts. And this is a document collection. And for the queries, these from the real-world user query, these queries are from the real-world user as well. So the users are describe their legal cases to the lawyers, and then the lawyers, make the note and summary these notes in the with the legal terms. So finally, they constructed 31 sample queries for us to conduct our research. And each query along with the keywords and some concept annotations. And here's the example of this, the query statement and the keywords they provided with us. The lawyers also helped us to highlight with the different colors to show the relations between these keywords with the part of the content of the query statement. And this is an example of of how the lawyers use the concepts and the core concept to annotate the queries. These concepts are from the taxonomy concepts and like shown in this blue color terms. And another called core concept, these are not from the taxonomy things. And these are, extracted by the lawyer themselves based on their legal knowledges. And they created 88 core concepts for us in total for this 1 million document collections. And they use this core concept to help us to annotate each of the sample queries as well. So we have the document collection and the queries now in order to build the whole text collection to conduct the the evaluation process. Another thing is that we need to have the relevance assessment for sure. So the general way is that the pooling methods could be used, to generate the relevance assessment by adopting the multiple search engines to generate the different ranked results and put them together. But here, since we have all these, different informations like the query itself, the keywords, the taxonomy concept, and the core concept itself. So we're thinking maybe we can use all these informations to generate the query variants to output the different ranking instead of using the multiple search engines to do that, to do the poolings. So here we do the pooling using the query variants, and we use all these features we mentioned, that keywords, synonyms, concepts, and the core concept to generate the eight variants for each of sample queries. And then we'll pass all these query variants to the Solr search engine to generate the retrieval results. And we took the top 15 draft documents from each variant's retrieval results to put them together. And finally, we have around 80 to 100 documents in the pool for each of the sample queries. Then, so we play with taking a different number of the documents from the multiple retrieval results, and we find that the 15 ones is the make sense and more reasonable ones to be used here. So next step, we're going to pass all these pooled documents for each sample queries to the lawyers to do the relevance judgment then. So again, for the general, that either the binary relevance judgment, either non-relevant or non-relevant, could be used, or the numeric relevance was 1 to 5 or 1 to 10. But here, when we discussed it with the lawyers, they present another idea. They want more specific, the judgment, relevancy judgment. So we are defining a new relevancy rating scales here. There are 4 relevance scales. The first is, it is what I'm looking for. So in this case, the lawyer will think this document is totally relevant to the queries, and they are definitely going to rate it because this is what they're looking for. And second relevance scale is called on topic relevant, but will not rate. So this case, the lawyer will think this document is relevant to the queries, but they're not going to rate it because this type of the documents are kind of the well-known documents, which the lawyer think they already know the content of this document, but they prefer to see this document appears on this top ranked list, but they're not going to rate it. So the third relevance scale is called on topic, but not relevant. And in this case, the lawyers will think the document is on the same general topic with the sample queries, but is not relevant to these query cases. And the fourth is just non-relevant at all. So they're definitely not going to rate this document at this relevancy scale. So when we provide all these relevancy scale to the lawyers, and first we gave them 2 sample questions to do the examination, and we ask at least 2 lawyers to examine each of the sample queries we gave, and we are quite surprised with the results we got. We received a large number of the offsite assessment from them, like the example here showed in this table. Here is for the query 29, and this query examined by two lawyers. And the pool size for the assessment documents contains 93 documents, and 69 of them received the different relevancy levels, and 33 of them received the total offsite relevancy, which means for these 37 documents, one lawyer thinks this is the relevant one, and another lawyer thinks this is the totally non-relevant ones. So in this case, we are discussed with the lawyer again because we need to seek their opinions, and they said they're not surprised because lawyers always have these distinct interpretations of the same query statement. So they present us, when we see the query, we just see the query itself, the statement itself. But when the lawyers see the queries, they just automatically see a piece of queries, like this. They separate the query statement into the different pieces. and each piece is kind of a subtopic. They are refer to a subtopic, and the different lawyers may focus on the different subtopic of the same queries to do the relevance judgment. So that's why this leads to a large number of offsite assessment results then. So based on this case, in order to not lose any of the, the relevant document in our relevance assessment, so finally we decided that for each of the sample queries, we asked at least a lawyer to do the relevance judgment. And if any of these lawyers think one document is relevant, we just go for the option that this document is relevant and to be marked as one in our relevance assessment then. So because this, the relevance judgment process is quite time consuming, and even for a very experienced lawyer, it will take them around 10 minutes to process one document. So after months of time, they finally access 26 queries for us. And also they find that around 25% in the pool for each query to be relevant. That's why they gave us a very positive feedback for our polling methods. Yeah, so now we have everything we need to do the evaluation. For the experiment, we just tried the very basic ones. 3 indexing methods are used here. The first is standard word level indexing, and another is concept indexing, because all the documents come with a list of the taxonomy concepts. So we were trying to index all these concepts instead of the documents as well to see what we can get, what kind of results we can get. And third is the fragment indexing, and we use a C99 to segment documents into the different fragments and index and retrieve them separately. And when we get the retrieval as a fragment retrieval list, if we find that multi-documents are coming from the same multiple fragments are coming from the same document, we're using 3 different ways to merge them together. So I'm not going to the detail of this to save some time then. So 26 queries are being used here for our experiment, and the BM25 is used as a baseline to do the comparison. And here's the results we got for the different runs, the baseline plus core concept and some others. And it's very obviously from this results list, the core concept ones performs really poorly. And after analysis, we find that that may be because there's very sparse concept annotations. And we think that if we have a very rich concept and annotation available for each document, it's worth to try this concept indexing methods again to evaluate whether this is good methods or not. And this core concept, based on these lawyers' personal legal knowledge extractions, this core concept is quite helpful for this legal retrieval tasks. And also fragment indexing performs overall best. It's obviously from this result see that. So the conclusion is that you can see that our experiment is quite basic and non-technical as well. So at an early stage of this legal information retrieval task, but we find that all this discussion made with the lawyers and analysis we did with them, and the findings we observed is quite interesting and quite valuable feedback for the legal information retrieval tasks. So unfortunately, this collaborations has been ended for half a year ago, so we can't do any further investigation on the same corpus, but we think that all these interesting observations, indicate some strengths and weaknesses occurred in the legal domains. And we hope that this work could suggest some potential directions for the further research conducted on this legal information retrieval tasks. So that's all. Thanks.
Yeah, any questions from the audience?
Hey, wait, can I ask a question?
Yeah, of course, Devashis.
Nice to meet you after such a long time. How are you?
You're good.
Well, that's not the question.
Oh, how kind you are. Thanks. I'm very good. How about you?
Yeah, I'm good. I'm good. Yeah, so I wanted to ask you. So I found it very interesting, right? So when you say that you talk to the lawyers, and then so basically, so if you go back to the slide about the 4 relevance scales, so I think the second one down your list.
Here.
So that's very interesting, right? Because it says that document is relevant, but the lawyer is not prepared to read that because he knows the content of that document, right?
Yeah.
This is quite in contrast to what we see in the standard ad hoc IR experiments. We don't try to model the users, right?
Yes,
this is very interesting because you have kind of talk to the users, and then you know their language model, and so you are trying to take into account the knowledge of that person, who is going to use that retrieval system, and then define the relevance accordingly, right? So this is quite different from what we do in standard IR.
Exactly. If we don't talk to lawyer, we will never know this.
Yeah, so I'm wondering if you can release the data sets, and then if we can, is this possible to use this data set in the community for research purposes, or?
I'm afraid no. We talked with them and they said it's quite private. Even anonymous, all these users' names, it's not allowed to release the data set.
Okay.
Yeah. So,
but I guess we can
this
do
idea is
like
quite
this on
interesting.
standard.
Sorry. Yeah. But we think this idea is quite interesting. So we are now is trying to seek some like the fundings to fund all these kind of the research on legal domains. If we could get the fundings, we could collaborate with some Irish local legal companies to continue doing this kind of research in the near future. We hope. Yeah.
Yes, because I guess this is very interesting because even on standard collections. We can redefine the relevance judgments by keeping into account, or by taking into account the user knowledge of when we are releasing the relevance assessments for one particular topic. We could do it for different users, right? So this will be kind of personalized relevance assessments that we could have, right? And then we could
that's true.
Code systems based on how personalized they are in terms of retrieving content.
That's true, but I have to say that lawyers is really hard to predict.
Good. Very interesting. Thank you.
Thanks. Very nice to see you again then.
Yeah, after a long time, yeah.
Yeah.
Any more questions? All right, I think we have. All right, so yes, so we have reached the end. Thank you, Wai. Thank you for attending.
Thanks very much.
Yep. So we have reached the end of today's session, and tomorrow we start at 4:30 p.m. IST. That's 11 a.m. GMT, and I guess it's 6 a.m. CET. Yeah. So yeah, we'll start with tomorrow's track presentations, and tomorrow we also have the first plenary talk by Dr. Ellen Vuris. So see you all tomorrow. Thank you.